which is defined on a graded vector space X, capital X denoted here, and you have a number of algebraic operation like a differential, which you can also view as a 1 bracket, and then a 2 bracket, a 3 bracket, and higher brackets, which have a certain number of inputs. So today I will discuss the relation to field theory in this lecture, and then discuss homotopy transfer either at the end of this lecture or at the beginning of the final third lecture. So let's begin. So basically there's a dictionary between L-infinity algebras and field theories, which looks as follows. So you have the chain complex, which is this sequence of vector spaces x1, x0, x minus 1. And you have the differential partial, which acts between the spaces. And in my convention, this has intrinsic degree -1, which means that you go from x1 to x0, from x0 to x minus 1, etc. So that's the basic structure we start with. And the field theory interpretation is that we view x0 as just the space of fields. So for any given field theory, you start by specifying the fields, and you think of this as parameterizing a space x0. Then you have the first differential acting between x0 and x minus 1. So I can put here a little subscript 0 to indicate on which space this acts. And that goes from the fields to the what I call here equations of motion. So that's just the space I have to introduce for the equations of motion to live in. And then there may also be higher spaces corresponding to Bianchi and higher Bianchi identities. And in the interesting case, I also have a gauge symmetry. So then I have a space x1 on the other side, which I want to think of as the space of gauge parameters. So schematically, collectively, I denote them here by capital lambda, and the space of fields by calligraphic A. So I have here a differential d1 that we will see in a moment, parameterizes or encodes the linearized gauge transformations. So the higher and lower spaces also have an interpretation to which we may or may not come. Okay. So let's begin by writing out the equations of motion. So the point is, as I briefly sketched at the beginning of last lecture, is that the equations of motion can be written in terms of the L-infinity structures. So they take this Morra-Cartan-like form, where the leading term is the differential. So that's the linear term. And all the higher order terms are defined by brackets. So I have the 2 bracket, the 3 bracket, and the principle continues indefinitely. So in other words, if I have those brackets, I can immediately write down the equations of motion. And the same is true for all other natural operations you do in field theory. For instance, I can write the gauge transformations in terms of these brackets. So the infinitesimal gauge transformation of a field curly A is given by d lambda as the leading term. And then I have higher order terms involving lambda and A. And since this is infinitesimal, I always have 1 lambda, but an arbitrary number of A's. So it continues like this. If I have a little more structure, I can also write an action. So strictly speaking, an action requires a little more than just a plain L-infinity algebra, and that's an inner product. So in particular, if I have what I introduced last time as a cyclic L-infinity algebra, that has such an inner product, and then I can write an action that looks as follows. So I have these angle brackets which indicate the inner product, and then I can write a kinetic term in terms of the 1 bracket or the differential. I can write a cubic term in terms of the 2 bracket, and it continues indefinitely. So the quartic term would need the 3 bracket, etc. So from this, you see that the 2 bracket on fields encodes the cubic terms, the 3 bracket encodes quartic terms, etc. So from this, you can immediately infer for a given field theory, what kind of L-infinity algebra you may or may not need. Okay, so this is all pretty abstract, and we'll discuss couple of examples as we move along. But let's stay at this abstract level for a little while longer, just to understand what the significance of this dictionary is. So that you can do various tests now. For instance, you could start transforming the equations of motion under these gauge transformations written in this form, in order to verify, for instance, that the equations of motion transform covariantly. And you can check that this works, and that precisely uses the L-infinity relation. So you never need to specify at this level of abstraction what kind of field theory you're actually working with. You could just insert these general variations and use the abstract L-infinity relations. And this holds true more generally for all kinds of checks we normally do in field theory, like checking closure of the gauge transformations, checking invariance of the actions. All these things are precisely encoded in the L-infinity relations. So in that sense, the concept of an L-infinity algebra is sort of the proper algebraic implementation of what we mean by consistent field theory. So that's discussed in the literature in various places, in particular in my paper with Barton. But there's one viewpoint which...
Olaf, can I ask something?
Yes, please.
Yeah. So is it the claim that in any field theory, the cubic term in the equation of motion will satisfy the L-infinity algebra?
That is my claim, yes. It's the kind of statement which you cannot prove, because there's no independent definition of what you mean by a reasonable field theory. But certainly the natural examples you can think of, we tested. And there's actually a sort of criterion for what you want to a reasonable perturbative field theory to satisfy that allows you to relate this to the L-infinity axioms. So the statement would be any consistent field theory should fall into this scheme. But then, of course, the unprecise part of the statement is what do you mean by a consistent field theory? And I'm trying to illustrate. I will try to illustrate this as I go along.
But suppose I say that any action, I mean, anything that can be written as an action will have this property. Is that the claim?
No, you can certainly write crazy actions like an action that has a gauge symmetry at the quadratic order but breaks it at the cubic order. Doesn't have a consistent extension. That would not satisfy the L-infinity relations. So you can certainly cook up examples that do not give an L-infinity algebra, but then the claim would be those examples you would never consider in practice. So that would be the extreme example would be that a gauge symmetry of the free theory is not preserved at the interacting level, or that a certain integrability of the field equations does not hold beyond the linearized, the free theory. That kind of thing.
I see. And if you have a theory without any gauge invariance, then does it always work?
Then it always works, yes. So that's actually the example. So maybe I should just do that example first.
Just a question.
Okay.
If you take a string field theory and you do the explicit calculation, you get this damping factor, which is exponential minus alpha prime second derivative. So it doesn't end. This kind of action doesn't fit what you are saying, does it?
Why not?
Well, because it is in higher derivatives.
Yeah. So the higher derivatives. I mean, I'm not sure in detail that kind of theory. I haven't looked at it, but higher derivatives in principle is no problem, because so this abstract differential I'm using here, that doesn't tell you it's a first order differential or second order. It can in principle be a higher order operator as long as it's compatible with gauge symmetry. So let me maybe start with this sort of most trivial example we can think of, and then later I will discuss other examples. So maybe it will become clearer what I mean here as I go along. Okay. All right. So let me then maybe just start with the example. So this is the most stupid example you can think of. It's just phi to the phi cube theory. So no gauge symmetry. So in this context, this L-infinity algebra is really an overshoot, but just to make this point very explicitly. So we write down a massive scalar. And we have a phi cube term. So the chain complex in this case is just given by x0, the space of fields, and the space of equations of motion, which in my convention is a degree -1. And then it just goes to 0. So this means there's only one differential, which is del 0. And that differential is given by del of phi. So since by the dictionary above, this is supposed to define the free part of the theory, the linear part. So this is just the Klein-Gordon operator on phi. And now I have to view this as an element of the space x-1. So this is something that at first may look confusing because phi starts out living in x0, has degree 0, and now I act with the Klein-Gordon operator, now it has degree -1. But that's exactly as it should be because the differential, which is now the Klein-Gordon operator, has degree -1. So that's just the degree counting I need to do in order to keep track of in which space each object lives for the graded commutativity to work out. So that's the only differential in the game. And now there's only a 2 bracket. There's only one 2 bracket, which is defined on x0, so between phi 1 and phi 2. It is given by
lambda phi square term also?
Excuse me?
So in this del phi equals to box minus m square phi, shouldn't there also be a lambda phi square type term?
No,
from the
so the lambda comes in the 2 bracket. So let me just write it out. Lambda phi 1, phi 2. And now, I've just, all I've done is I've defined the objects in such a way that the full equations of motion for this model are just given by this Maurer-Cartan form, del phi plus 1 phi equal to 0. So, and here you can also check that the grading works out. So phi 1, phi 2 lives in x0, so they have even degree. So the bracket is actually symmetric because in general it's graded symmetric. So that is given by phi 1, phi 2 makes perfect sense. And trivially, so at this level, all I've done is I've took the equation, I gave a name to the linear piece, to whatever multiplies the phi in the linear piece. I called the differential the Klein-Gordon operator, and the quadratic piece I've also given a name, a bracket. Now the claim is that this defines an L-infinity algebra. It just happens to be the most boring one kind of L-infinity algebra you can think of, namely where everything is just trivially true. So if you want to check the L-infinity relations, well, first of all, you have del squared equal to 0. That is trivially true because there's only one differential up here. So you sort of, to be more formally precise, you could say, well, there's one differential here, which is del 1, and then another one here, which is del -1, but they are just equal to 0 because they're mapped to these trivial spaces. So whenever I compose 2 differential, I get trivially 0 because only one of these differentials can ever be something non-zero. So that is trivially true. And the same follows for the higher L-infinity relations. For instance, if I take the Leibniz type of relation, I want to check that the differential on phi1, phi2 moves through. Well, what is this? So phi1 and phi2, that lives in x minus 1. I should have said this here. It's again by degree counting. So phi1 and phi2 each have degree 0. The bracket has an intrinsic degree of -1. So this lives in x minus 1. And again, you shouldn't be confused by the fact that the explicit formula is just the product of two phi's living in x0. That's just the counting we have to do to work properly with these relations. So since the bracket phi1 with phi2 lives in x minus 1, the differential acting on it is trivially 0. And the same will turn out on what's written on the right-hand side. So this is supposed to be up to a sign in my convention, d phi1, phi2 minus phi1, d phi2. And again, this lives in -1, 0, 0, -1. And there's no bracket that has an non-trivial bracket that has an entry in -1. So these are individually 0. And you can just check by degree counting that all the higher L-infinity relations are just trivially true. So you never get a constraint on this field theory from the requirement that this should be an L-infinity algebra. And that's precisely related to the fact that there's no gauge symmetry here. So interesting examples for L-infinity algebras only come when you have a gauge symmetry. And in that case, you get non-trivial constraints for higher interaction vertices, for instance, from the requirement that this should be an L-infinity algebra. And the claim is that these constraints are exactly of the kind that we always impose in field theory, typically that the gauge symmetry of a free theory is preserved by the interactions. I hope this clarified a little bit the philosophy here. Are there any questions on this example?
With a 5 to the 4 or 5 to the 5th without lower terms, how would you get the equation of motion?
Well, I mean, you mean from each side. Well, from the action side, we know how to get the equations of motion.
Yes, but from the bracket, because from the two bracket, I would have some.
Well, it's just what you do is, I mean, it's so trivial that it's hard to understand apparently. So you work out, give any action, you work out the equations of motion. And the only assumption is really that there's a perturbative scheme, so that there's a definite notion of the terms of the action being quadratic, cubic, quartic, etc., and the same on the level of the equations of motion. Once you have that, you just read it off by comparing this formula here. You say the leading piece, the linear piece, defines the differential. The quadratic piece defines the two bracket. The cubic piece defines the 3 bracket, etc. Now, there's one technical point that I should have made here, is that these brackets, of course, in general, are defined on general arguments where not every entry is the same. But you can actually, in this case of the equations of motion, convince yourselves that you can always reconstruct using the graded symmetry from this bracket evaluated on the same arguments, the general bracket. So in other words, you can extract by these so-called polarization identities the bracket on an A1, A2, where A1 and A2 are arbitrary, from the bracket of A with A. It's exactly the kind of relation used to relate the quadratic, to reconstruct the scalar product, general scalar product from a quadratic form. But once you up to this point, you just read it off from this dictionary.
Okay, thanks.
Okay.
I have a question.
Yes.
Yes, so in that part of the gauge transformation, please. So
Yeah.
if in the case of, for example, Young-Mills, you can only go up to the second bracket, right? To the
3
product
bracket
of lambda with A.
So I will discuss actually the Young-Mills case explicitly. In this case, you will have you will have a 3 bracket on fields, which comes from the quartic vertex of Young-Mills. But that's the only 3 bracket in the whole algebra. So in particular, you don't have a 3 bracket where one entry, like this one here, where one entry is a parameter and 2 entries are fields. So that's another point one has to get accustomed to. This 3 bracket here that I just underlined, which has 1 entry parameter and 2 entries fields, is completely uncorrelated to this 3 bracket with 3 A's. Of course, there are relations coming through the L-infinity relations, but it's not that there must be a universal formula that gives you all 3 brackets on some kind of general form, so that whenever you have a 3 bracket on fields, you must also have a 3 bracket on parameters and fields and things like that. So that hopefully will become clear with the Young-Mills example.
Yes,
okay.
and will you, sorry?
Yeah.
So will you talk about finite gauge transformation on this language also?
No, I won't.
Okay, thank you.
Okay.
Sorry, this phi cube theory example is an example of a differential graded Lie algebra because you don't have any 3 bracket onwards.
Right. So this is actually a differential graded Lie algebra. So it has sort of this Chern-Simons-like form. But of course, the point I'm making here is true for whatever scalar interaction you would include. If you have phi to the 4 theory, you do have 3 brackets and so forth. Okay. So let me.
Olaf, one more question.
Yes,
is the existence of L infinity related to the existence of BV formalism for these theories?
Well, the other way around is certainly true. If you have a BV formalism, there's a associated L-infinity algebra. I suppose it's also true the other way around. If you extend your concepts suitably. So, in other words, you introduce anti-fields and all these things as explicitly as fields and write the corresponding BV action, etc. So I think the answer is yes.
Okay, thank you.
Okay. All right.
But
so
the other way around is if you have, for example, some equation that doesn't have an action, you can have an L-infinity formulation, but you cannot go to any action in that way. So there is no always.
Yeah. So in that
other
sense,
way around.
Right. So one has to be careful with trying to make a precise, 100% precise statement here. It is conceivable that you have L-infinity algebras where you have consistent equations. I mean, the basic point is that the concept of an L-infinity algebra is something more basic with less structure than what you have always given in the BV formalism. For instance, the cyclic structure that I assumed here in order to write an action is not part of the basic L-infinity algebra. It's an extra structure that may not exist. So in principle, indeed, you might think of examples where this is not the case. It's just so, of course, the usual field theories we think of do have an action, and usually that's something we want. Okay, so
has anybody studied if these higher spin equations somehow have underlying L-infinity algebra? Because those don't have known equations or known action.
Yeah, that's a good question. So there isn't, in fact, there are some comments in the higher spin literature on some underlying L-infinity structure for the Vasilyev higher spin equations. And now I remember now that Barton and I had some correspondence with Vasilyev when we wrote that paper. But I'm afraid I won't be able to make a very sharp statement now. There's some relation between higher spin and L-infinity, but I'm not expert enough to really say this precisely.
Okay, thank you.
Okay, no problem. Any other question? Okay, so if not, then let me make the one general point which I think nicely illustrates the point of the L-infinity relations, which is related to the solvability or integrability of the equations in this form. So as I said, in general, you could write actions, those random interactions that do not define an L-infinity algebra, but then there's some basic things wrong. There's something basic wrong with these equations. And this can be illustrated as follows. So let's look at the equations again. So let me just write it as a straight A now. So suppose I look at the equations, and let me introduce an explicit coupling constant G for counting. So G goes with the interactions. And I want to ask now the question, can I always solve these equations perturbatively, at least? And the point I want to make is that this is true if you assume that these brackets are really L-infinity brackets, but not otherwise. So I do the usual ansatz. I want to solve this for A perturbatively in G. So I have a 0th order solution. I have a 1st order solution with a G. And I have a 2nd order piece, etc. And now if I plug this into the equations of motion, I get a 0th order contribution, which is that, of course, that partial of dA0 should be 0. So not much to see here. Then I get a 1st order equation by collecting the terms linear in G. So that's, of course, there's one contribution d of A1, which is linear in G. And then there's one contribution when I insert the A0 into the 2 bracket. That is also proportional to the G, and the overall G is scaled out. So then I get plus 1/2 A0 equals 0. And then let me do one more step. Let me look at the G squared terms, which are the most interesting from our point of view, where you have several contributions. First of all, you have the 2nd order contribution to the field, the A2. Then you have 2 contributions of G squared where you insert one A0 and one A1 into the 2 bracket. Now, because by the graded symmetry, they give the same contribution. So I get a plus 1 A0 A1. And then I get one contribution of order G squared that comes from the 3 bracket, where all these A's are A0. So I get a plus 1/3 factorial A0 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 equal to 0. Okay, so that of course continues now indefinitely, but let's look at these first 3 equations. So let's assume I solve the first equation at order G to the 0. So I have an A0 now. So the point I want to make is that I get now non-trivial integrability condition at order G that is obtained by acting with another differential. So if I act with another partial, I get partial squared A1 plus 1/2 partial acting on A0 with A0. And this must be 0. Now the first term is just identically 0 because the differential squares to 0. So A1 is the object that I really want to determine, assuming that A0 is already given. But in this integrability condition, A1 just drops out no matter what it is because the differential squares to 0. So I get a condition that is that the second term should be 0. Now, if you look at it, that looks a little funny because it only involves the A0. A0 is the object that in this perturbative scheme already determined. So I don't want to find a new equation for it so that I would have to go back and fix the A0. So this should not be a new equation or a new constraint on A0. Or in other words, if I had a new equation on A0, this would sort of not be integrable, and this would be a kind of funny theory. Now, in this L-infinity language, of course, we can quickly see that we are safe because I can use the L-infinity relation, the sort of Leibniz relation. So I can move the partial inside, and I get two contributions of the same type. So I get a factor of 2. And this I know now is 0 by the equation that I already solved, the 0th order equation, partial A0 equal to 0. So the integrability condition is satisfied by virtue of this Leibniz relation of the 2 bracket. Okay, so that's good. Now let's see what happens at order g squared. So I act again with the differential. So I get differential squared on A2. Let's just look at the equation. This is the equation I want to look at. So I act with a differential. I get differential squared A2, which of course will be 0, plus differential acting on A0 with A1, plus 1 over 3 factorial differential acting on the 3 bracket of 3 A0s. Okay, and that will be 0. So as before, now I should think of A0 and A1 being already determined. I want to determine A2. But in this integrability condition, A2 drops out, no matter what it is, simply because the differential
Olaf, we can't hear you anymore, I think. Can someone else hear Olaf or?
No, I
cannot hear it.
And you can see that his screen is frozen from the time in upper left corner.
Yeah, at someone I could still see his screen moving, but not here. So I guess he has some problem.
Can you see my screen?
Yes, we do.
Okay, so where did I lose you? Which point?
Where you were starting to explain the integrability of the last equation, just
g squared. Okay. So what we're doing here is we look at the order g squared equation and act with another differential. So that's what I wrote out here. So I have partial squared on A2, which of course is 0, no matter what A2 is, because the differential squares to 0. And then I have these two terms with differential acting on A0, A1, and the 3 bracket of 3 A0s. Okay, so let's see what happens. Now, of course, as before, I have to use the L-infinity relations. So in this 2 bracket, I can move the partial inside up to a sign in these conventions. So here I generated term partial A0, which is 0, by the lowest order equation, and I get a term partial A1. Now this I cannot set to 0 but I can use the second equation, this one here, which I assumed is already solved. So I can express this in terms of the bracket, the 2 bracket. So what's left here is equal to 1/2 A0 with the bracket of A0 is A0. Okay. So now I've manipulated the right-hand side to have 2 contributions, this one here and this one that's left here. And now if you remember the L-infinity relations from last time, that's exactly the kind of relation that we can use. So this one underlined term is something like the Jacobiator of the 2 bracket, where all 3 terms actually give the same sign because the A0s are all of an even degree. So they all sum up with an appropriate combinatorial factor. And that is not 0, but it's actually controlled by the 3 bracket. More precisely, it's controlled by the total differential of the 3 bracket and terms that involve the 3 bracket of a differential. So just to write this out. So this is not by itself 0, but by the Jacobi-like L-infinity relation. This can be rewritten as del A0. A0, so there's 3 such terms which add up. So that follows by the L-infinity relation, but now I can use again that A0 actually satisfies that this is 0. So this is 0. So that means these equations are integrable. And so you see that the very natural requirement that we, maybe not exactly in this language, but typically assume in field theory, that the equations are reasonable in the sense of being integrable, that actually is naturally implemented automatically by the L-infinity relations. So that's one way to see that if you just write a random action, assuming that you have gauge symmetries and hence Bianchi identities, does not lead to an L-infinity algebra, but for any natural class of theories where you have this integrability condition, you do have an L-infinity algebra. Okay, any question on this part? Are you still there? Just to make sure.
Yes, we're here.
Okay,
in fact, I have a small question, maybe.
Yeah.
A bit related to what Ashok asked. So I think there is a theorem saying that if the linear gauge transformation is, del of mu equal d mu of lambda, then you know that it's a U1. So in principle, you can do a field redefinition to go just to this gauge transformation. You know how it works with L infinity? Like, do you preserve some L infinity structure, or?
You mean how you prove an L infinity language
if you want
theorem?
if you want to get a canonical gauge transformation, okay, I guess it would work only with U1. So,
well, I'm not entirely sure what you have in mind with the U1, but if you look at the literature and, for instance, proofs regarding the uniqueness of Young-Mills,
yes,
or the uniqueness of general relativity, so you start with the free theory with its abelian gauge symmetries, and then you want to make the point that the interacting theory is for spin 1 must be Young-Mills, or for spin 2 must be general relativity. You have to make, of course, some assumptions, and I think the most general such proof is due to Wald, both for spin 1 and spin 2, and he uses exactly this kind of reasoning, where we impose an integrability condition on the equations that follows from the effectively follows from the gauge invariance of the free theory and the Bianchi identities. So he doesn't do it, of course, in the language of L-infinity algebras, but the L-infinity language gives you a natural framework to express that in a simple way. So.
Okay, so yeah, in fact, it's what I had in mind exactly. So, like for example, if you had a theory which would add a more complicated infinity algebra, you could also just follow this reasoning and simplify to get the canonical Young-Mills or general relativity, right?
Well, I mean, if you have a more complicated looking theory that, however, it's just the rewriting of Young-Mills or general relativity by some horrible field redefinition, then I think the statement must be that there is an L-infinity morphism from that very complicated L-infinity algebra to the simple one. Now, how you would find that in practice, I don't know. So the L-infinity viewpoint is not like a magic box that allows you to do things that you couldn't do otherwise, but it's mainly a framework to sort of very much systematize and express algebraically the things that we are familiar with in field theory anyway.
Sure. Okay, thanks.
Can I ask a little bit more?
Sorry.
Sorry.
Yes.
Can I ask a little bit more? So the claim is that this L-infinity structure is covariant under field redefinition?
Well, the question is what exactly you mean by covariance, but
it means
I would say that if you mean an
L-infinity
L-infinity structure goes to an L-infinity structure, then I would say yes.
So in the BV formalism, I would say you would have to have some transformation that is canonical with respect to the anti-bracket. So I'm not sure whether that features here at all.
Well, I mean, I'm not saying you can consider completely general transformations. They should be reasonable, and reasonable means they can be viewed as an L-infinity morphism, as I defined yesterday. So that should include all possible invertible field redefinitions. So a field redefinition, so in other words, an L-infinity morphism where the leading term, the linear term, is actually in an isomorphic invertible map between two spaces. And then the whole thing.
You may also require some compatibility with respect to the inner product, right? Or
well, that's when you care about an action.
Yes.
So if you don't care about an action, you just ask about the classical equation of motion and all these things, which is really what the bare L-infinity algebra encodes. Then you only care about L-infinity morphisms.
Okay.
But you're right. If the action is involved, then you get more requirements.
Okay, thank you.
I mean, one point may be that if you take an arbitrary field definition of the fields, then you can always try to find appropriate transformation of the anti-fields so that the BV structure is preserved, the anti-bracket is preserved. But here, since you're only considering transformation of the fields, maybe you don't see any constraint. That any transformation of the fields, you can lift to an L-infinity morphism.
Yes, as long as it's an invertible transformation. So you go to a new field basis, but of course you should always, if it's not invertible, then it's just degenerate. But other than that, I don't see.
Yeah, but I think once you introduce the anti-fields, that's probably not going to be possible, I would think.
Okay.
As Ed was saying that there will be that you have to preserve the anti-bracket structure. I'm not sure.
Okay, maybe. Was there another question?
Yeah, one question. So, like yesterday in Barton talk, we saw that this geometric Boxster equation has an obstruction to a solution under certain conditions. So, does these equations also have like similar conditions when it will be solved, when it can be solved? Like this A0, A1, when can we get a reasonable answer? Is there like any constraint or condition on this?
Well, I mean, this is this discussion I did here started from the assumption that you can solve the very first equation. So
but here you have just like done a perturbative expansion of A and written like perturbatively what the equation is.
Yes. So So if there's no obstruction to the perturbative solvability of this equation at higher order. That's what this analysis shows. Now, okay, maybe that's a good point for the discussion session. We can discuss with Barton what exactly the relation to that point of view was.
Olaf,
yes.
I would imagine that you're checking integrability, but in some sense you have to know that there's no cohomology there, like the fact that D of the rest vanishes is necessary, but it's not sufficient. But perhaps because you're working in flat space and no topology, there's just no question that any closed form is exact, and therefore there's always a solution. So presumably the cohomology groups vanish here. I would imagine.
Well,
okay, thank you. Yes,
so I want to think about this for a few minutes. So maybe we can come back to this later. I'm sure there's no problem in this discussion here. But I'm not entirely sure what's the precise statement to relate the two. But let me come back to it later. So
this was essentially my question as well. So I don't.
Okay. There was another question, but it's already covered. Okay. So in the second part, actually, the homology will play an important role. So let me think about this point for a few minutes during the break. But let's finish the first part, and then we can maybe come back to it later. So I just want to finish the first part, lecture 2, with the second example, which is just Young-Mills theory. Example 2. So we start as usual with the chain complex. So I have a space X1 of the gauge parameter. So this I call lambda again. And for Young-Mills, of course, this is a zero form that takes values in the Lie algebra of the gauge group. So the Lie algebra indices I will always suppress. Then I have the fundamental field, which is a Lie algebra valued one form, A mu. And then I have a partial 0 to the space X minus 1, which, as before, we want to take the space of equations of motion, and I denote this by this calligraphic E. So you should think of this as an equation of motion. And then in principle, we can introduce one more space, X minus 2, which is where the Bianchi or Noether identities live. Okay, so as usual, we start by defining the differential. So partial 1 acting on lambda. So this goes from X1 to X0. So it goes from the 0 forms to the 1 forms. So let me indicate it like this. So it takes values in 1 forms indicated by an index mu. And that's just partial mu lambda. So the first differential is just the de Rham differential, in fact, on a 0 form. So that's how you would expect it. But the next differential is more interesting. I mean, it's not particularly interesting, just to make the pedagogical point that there's no correlation a priori between the order of differential operators that are involved here. So the next one is just the linearized part of the Young-Mills equation, or the same as the Maxwell operator, because I suppressed the color indices. So all these A mu's and lambdas take values in the Lie algebra. But of course, at this order, it doesn't show up. So here I just define this to be the second order differential operator that defines the linear piece. And then finally, D minus 1 on E is just the divergence of E. So the equations of motion is an object with a free index, and I take the divergence. So that these are my definitions. And now you can check that D squared is 0, which is now encodes two equations. One is partial 1 composed with partial 0 equals to 0. So for this, you take the first differential here and you plug it into the second and you get 0. And that's, of course, the statement of linearized gauge invariance. So the linearized Maxwell equation obeys linearized gauge invariance, trivially so. And then you have a second equation, non-trivial equation under partial squared is 0, which is that the composition of partial 0 with partial minus 1 is 0. And that's just the Bianchi identity or Noether identity. So if you take the divergence of the Maxwell equation or of the free part of the Young-Mills equation, you get 0. So that's the composition here of D minus 1 and D 0. You see, if you take the divergence, you get 0. And that's, of course, precisely the kind of equation that one uses to derive integrability conditions, for instance, for the Young-Mills equations. And that is part of these standard proofs in the literature to show that an integrable and hence consistent extension of the free theory must
partial minus 1.
Sorry? Are you still there? Hello? Is the internet gone again?
I think Ashok got disconnected.
Ashok was gone.
Okay, wasn't me. Okay.
I think you can continue, and when he comes back, he will ask.
Okay. Okay, so my internet is not the only unstable internet. Okay, so these are the differential. That's the chain complex that defines the free part. And now let's write down a couple of two brackets. So there's the two bracket. Now let me use the notation B2, B3, etc. again. So I have the two bracket between two gauge parameters. So these live at degree 1. If you go back to the table here, the chain, these live at degree 1. And that's just given by the normal Lie bracket, the Lie bracket of the gauge algebra, the gauge group. And that, again, lives in X1. So this is closed. So you have two inputs in X1. B2 has intrinsic degree -1, so the result is also in X1, and hence it's antisymmetric. And that's, of course, as it should be, because the gauge algebra, you want to be an antisymmetric bracket. So that's exactly as you would expect it. Now, the notation is a little, it's not precise enough, really, because I use both the square bracket and the B's to indicate these brackets, but now the square bracket is really the bracket based on the Lie algebra of the gauge group, which for this bracket coincides, but in general may not, which you already see at the next example, because now I've had the two bracket of a field, A mu, with a gauge parameter lambda. Now this is something that has one entry of degree 0, one entry of degree 1. So it's actually graded, since it's graded symmetric, it's actually symmetric. So this is equal to B2 of lambda A mu by definition. And both of them I define to be, now it's the commutator, the commutator of A mu with lambda in X0. So that's the kind of equation that looks at first a little funny, because A mu with lambda, you think if you exchange the order, you get a sign, but on the left-hand side, you don't. But that's just the definition. You just mean by both objects, B2 of A lambda and B2 of lambda A, the same object given by this Lie bracket of A mu with lambda. Then you have B2 of an equation of motion with lambda, so object at degree -1 at 1, And this is also given by the Lie bracket up to a sign, if I'm not mistaken, which lives in x minus 1. And now the most interesting part is the 2 bracket of A is A, so 2 fields, and that lives in the space of the equations of motion. So it has also one index, let's call it mu, and that's given by 2 partial nu, A mu, plus 2 partial mu, A nu, minus partial nu, A mu, A nu. Now, where does this come from? Let's do a few checks. So the check is simply that under this dictionary, you get the usual stuff. So the gauge transformation delta A under the dictionary is supposed to be B1 lambda plus B2 lambda A. So if I put the mu index back in, you can just check, well, B1 lambda was of course just d mu lambda. So that's what you would think, plus B2 lambda mu is A mu lambda, the Lie bracket. So that's just the familiar gauge transformation. And similarly for the equations of motion, I want del A plus 1/2 B2 AA plus potentially 1/3 factorial B3 AAA. And the actual Young-Mills equation, of course, is this, is d mu f mu nu equal to partial mu f mu nu plus commutator a mu with f mu nu. So the leading part, you probably know by heart, is just given by this differential. Here, that's just the leading part. So you don't have to worry about that. But if you look at the quadratic piece, what you will get. So we get one contribution from d mu acting on the commutator term inside f mu nu. And then I get one contribution where the f mu nu and it's inside the commutator is the abelian part. And that's exactly the structure of these terms here. So the factors 2 is just to compensate for the 1/2 in the dictionary. And so that gives precisely the quadratic terms in the equations of motion. But of course, there's also a cubic term, which is the final one, a mu commutator, a mu, a nu. And that's the reason why there's also 1/3 bracket for Young-Mills. The only 3 bracket for Young-Mills is defined on fields. So there's no 3 brackets with gauge parameters. And that just means that the gauge algebra itself is just a normal Lie algebra, nothing higher. But that doesn't exclude the possibility that on the fields, you have a higher algebra structure. And that's encoded in this 3 algebra, 3 bracket. So yeah, something like this. All right, so you can verify that all these L infinity relations I wrote down last time are actually obeyed for this example. And if you check all these L infinity relations, you sort of realize that what you're checking is just the part of the normal homework exercises you do in field theory when you're asked to verify that the Young-Mills equations are gauge invariant or that the gauge transformations close according to the bracket, etc., etc. So in that sense, it's basically an organizational tool or an organizational principle that breaks up those computations into small subpieces and gives a neat algebraic interpretation to this. So I hope with these examples illustrate a little how this works. And I think it's time to stop anyway for a small break.
May I ask a question before we end? Suppose I give you Young Mills in Bertal-Vilkovilsky formalism, where there are not anymore any gauge parameters. How do you do? Is it the same as the 5 to the cube example, or what?
Sorry, what do you mean without any gauge parameters?
Because if you take Young Mills and you reformulate Young Mills using the Bertal-Vilkovilsky formalism or BRST formalism, which is the same, you get the theory is not anymore invariant under gauge transformation, but it has a global transformation. So
well, but the gauge transformation is still there, right? I mean, it's still part of the formalism.
No.
Sorry?
No, it is not there. There is a global symmetry. It is not a gauge symmetry anymore.
Okay.
Let us discuss after a break.
Yeah, I guess so.
Okay, thanks.
So I suggest we take.
I have another question.
Oh yeah, yeah, sure.
Yeah, you defined this partial -1 on the equations of motion.
Yes.
So was that motivated from something, or it was just written down so that it works?
It was basically written down so that it works, or you realize there's. I mean, you also, in fact, you can cut off here if you want, and then you still have a differential that squares to 0. You can still define an L-infinity algebra, but this is a natural extension, yeah. I mean, I'm not sure if I can give a deeper reason for. It's sort of obvious in this example why this is the right thing to do. I don't think I can give a deeper reason at this point.
I see. Okay. Okay. Thank you.
May I ask a question?
Yes.
Which is related to Ashok's question. So is this a unique L-infinity algebra for the given Young-Mills action, Young-Mills equation motion?
Well, there are several. I would say no. I mean, first of all, there's several more minimal versions of L-infinity algebras. So, for instance, given Young-Mills theory, you can just zoom in on the gauge algebra itself, and that's a consistent L-infinity algebra by itself. In fact, it's just the original Lie algebra of the gauge group. So it's a trivial example of an L-infinity algebra. But then you can sort of extend it step by step. So, for instance, you can add in the fields, but you could cut off here. So you could say you include the gauge transformation of A, but you don't want to know anything about the equations of motion. So basically you're only interested in the off-shell structure. And in this case, that's also an L-infinity algebra. And so there's sort of a chain. Sure, chain is the right word here, but a sequence of L-infinity algebras of increasing size, one is subalgebra of the other, that encode more and more information of the field theory.
So, okay. So are they all related by affinity morphism?
I think so. I mean, I would say they even, I'm not sure what's the mathematically precise statement, but I would, in this case, even think it's, they're just subalgebras, strictly subalgebras, where you just, one is obtained from the other by setting a bunch of objects and brackets to 0.
Okay, thank you. That's interesting. Thank you.
Okay, I have one perhaps related question.
Yes.
Suppose you just have abelian gauge theory.
Yes.
Formulate it in terms of F mu nu and not. You just write down the equations of motion and the Bianchi identities explicitly as equations.
Sorry, Ashok, you're breaking up. I didn't quite understand.
I'm saying that suppose you take abelian gauge theory, just U1.
Yes.
But formulate the equations of motion in terms of F mu.
F mu nu.
Yeah.
Yeah.
So write down the equations of motion and the Bianchi, and never talk about A mu.
Okay.
So can you formulate that in the L infinity language?
I would think so. So you write down let's see, how would you do that? So you want to write the theory in terms of F mu nu as the elementary field.
Yes. Yes.
But then you put an equation, which is that that the curl is 0.
That's right. Yeah.
Okay.
It's basically like writing in terms of electric and magnetic field.
Yes. Yes. Well, I mean, you could just say this is a well, it depends on which equation then you want to put for. So, I mean, for instance, if you want to do Maxwell that way, then you would say you have these two equations, right?
That's right. Yeah.
Well, you could just declare this to be. Okay, how would you do that? Yeah, I'm not sure. I'm not sure. I would have to think about it. So you have no gauge symmetry. Yeah, I'm not sure. I mean, it doesn't feel very natural in this language, but I have to think about it.
Okay, thank you. Yeah, it's just that this doesn't have an action, so but we know it's a consistent set of equations of motion.
Yes.
Right, so it will be interesting to see if this can be formulated in their infinity.
Yes. Yes.
Okay, thank you.
Okay, thanks. More stuff to think about.
I think in that case you have an L infinity algebra, but not a cyclic L infinity algebra.
Well, I'm already wasn't immediately clear to me what's the differential. I mean, you could say that the space of equation of motion has two components. It's a 3 form and a 1 form. And one component is the curl part, and one component is the vector part. Of course, you can also dualize in a given dimension. So, I mean, I'm sure you can write something down. Question is what exactly you want to do with it, and what is the most natural formulation for that purpose.
So I think the break is over officially. So do you want 1 or 2 minutes break for you, or is it fine to start with the next lecture?
I would appreciate a little break. Maybe
Okay.
can 5 minutes or so to quarter past.
Perfect.
Okay.
Okay, so let's start again in 5 minutes.
Okay. Yes.
Yeah, so if we write this in terms of F mu nu, then the fields won't be element of x0 anymore, right? It will be of higher degree, right? Or does that make any?
No, I think the fields F would now be the fields. I think that would still be of x0.
Okay. That's how we'll define the degree kind of.
Yeah. Yeah. Okay. All right. So this is now the third part. On homotopy transfer. So what's homotopy transfer? So suppose we have now 2 chain complexes. I have one called X. let me just write it generically like this. So I have a space xi. Sorry. Xi plus 1, xi, xi minus 1, etc. And the corresponding differentials. And now assume that there's a second chain complex, which I denote by a bar, with its own differential, which I denote by partial bar. And let's assume that there are maps between these two spaces from x to x bar, which I denote by P. So you can think of this as a projection to begin with. So I want to think of x bar as a smaller space than x. So in the simplest case, it's just a normal projection. You go from a larger space to a subspace. And I now want to ask the question, under which conditions is a nice algebraic structure on X transported to an algebraic structure on X bar? And that's one way to motivate L-infinity algebras. So in order to state these conditions, I have to introduce a little bit of notation. So we have these projection maps, and I also want to introduce maps going in the other direction, which are called inclusion. And I denote them by iota. And I also want to assume that the P's are what's called chain maps. So they satisfy the condition that if I do a projection and then act with a differential, it's the same as if I first act with a differential and then with the map P. Okay, so that's one thing I want to assume. And then I want to assume that the composition of inclusion and projection in this form gives the identity on X bar. So if you want to think of X bar as a subspace of X, that is obeyed if you think of iota as the inclusion. So that just means you take a vector in X bar, you view it as a vector in X. That's what we mean by inclusion. And then you project down again. But since you started out with the vector in the subspace, you get back to the original vector. So this composition is just the identity. Now, if you had an identity in the other direction, of course, this would just be an isomorphism, and you could just go back and forth. But this, in general, will not be true. And that's where the strength of homotopy transfer and the language of L-infinity or other infinity algebras comes from, is that we can transport algebraic structures between spaces that are not isomorphic. So the right notion to consider here is, you might call this, I think, homotopy equivalence. Is the condition that the composition iota P is what's called chain homotopic to the identity. So this is the relation that iota P is not equal to the identity on X, but the failure for this to be equal to the identity can be written in this form, partial H plus H partial, where H are now maps that go in the opposite direction of the differential. So they're degree +1 maps in my convention. So they go in the opposite direction to the differential. So if you can define such maps H such that this relation is satisfied, for degree +1 maps H, then we have the basic setup of homotopy transfer. And the significance of this relation is that then the homologies are equivalent. So what are the homologies? So we have, whenever we have a chain complex, a differential that squares to 0, we have the notion of homology. Which is the vector space Hi, given by the kernel of the differential on Hi, on Xi, modded out by the image of the differential. So my convention, partial I plus 1. And more specifically, or more concretely, this is just the set of all equivalence classes X, where X is a vector in the big vector space X, which is closed. And the equivalence class is defined as you would expect, so that everything is the same if it differs only by something exact. So that's the notion of homology, or cohomology, depending on your conventions. And the statement is that if you have this homotopy equivalence, you have this boxed equation, and you can check that the homologies are actually the same. So then you have an isomorphism between the homologies on X bar and on X. So while the total spaces may be very different, the homologies are the same under this assumption. And under this condition, it is possible to transport an nice algebraic structure on X to a nice algebraic structure on X bar. So for the example we're interested in, that's an L-infinity algebra on X becomes an L-infinity algebra on X bar. So let's see how that works concretely. So I will call this the transported L-infinity bracket. So let's look at the simpler case just for definiteness. That X is a differential graded Lie algebra. So that means it has a differential and has a 2 bracket, and then it stops. In fact, that's a nice way to introduce L-infinity algebras. You start with something nice and simple, like a differential graded Lie algebra, and then you ask, what does this become under homotopy transfer, where you go to a different space in such a way that the homology stays the same. And the answer is, this is possible, but you don't get a DGLA anymore, you get a Lie infinity or L-infinity algebra. So then we get a genuine L-infinity algebra on X bar, the smaller space. So how are the L-infinity brackets defined? So let's say we take 2 vectors of the smaller space, X bar, and I put a bar on everything on this space. And let's say I want to work out, well, the differential I don't have to worry about because that was already part of the setup that is assumed to exist on the Barton space. Now suppose I want to work out the 2 bracket. What's the 2 bracket on X bar? Well, the natural operation I can do is I can first take the inclusion map to map these into vectors in X. So I will use the notation where I just leave out the bar when I do that. Sometimes confusing, but otherwise you go crazy with all those inclusions. So I map them up to the space X. And then on this larger space, of course, I can just take the 2 bracket. I can evaluate X comma Y in order to define B2, the 2 bracket on X bar. But it doesn't quite work, of course, because if I take the inclusion, I move it up to X, I evaluate there the 2 bracket, that in general will not be in the subspace anymore. So I have to project down. So this is, I have to include a projector like this. So that's really the only thing that makes sense and that I can do. So that should be the 2 bracket on X bar. But of course, you see what's happening. Since I've inserted here this brutal projection, in general, the Jacobi identity will not be obeyed. And that's the very reason why we go beyond Lie algebras. So let's work out the Jacobi relation. So that's called the Jacobiator. So I want to work out what is B2, nested with B2, x1 bar, x2 bar, x3 bar, plus cyclic terms, so the three usual terms. Well, let's write this out. So let me write out the first B2. So that is by this definition here, given by the projection acting on the bracket of, I had to do the inclusion of the second B2, and the second B2, let me keep this for a second. So it's like this. And that's the bracket with the inclusion of x bar 3 plus cyclic. And now let me write out the second B2. This is a projection of x1, x2, where now by leaving out the bars, I just mean that the inclusion was applied. And so I get something like this. Okay. Now the problem is, ideally, I would like to reduce this to the Jacobi identity on X, but the combination here I obtain is not the Jacobi identity of the kind of the Jacobi identity on X, because of this IP combination included here. And IP is not equal to 1. However, I have that IP is equal to 1 up to these correction terms that involve the homotopy map. So up to these terms involving the map H. So I have to use this relation. So this is the identity plus del H plus H del. So the terms with the 1, well, this is now just the Jacobiator on X. So that's what the projector X is, just the Jacobiator on X. So that is 0. So that term actually will drop out, assuming that I started out with a normal graded Lie algebra on X. So that's nice. So that term drops out by Jacobi on X. But of course, I'm still stuck with the other two terms. So I'm still, I'm not getting 0, but I get something that looks like this. So I have a term with a partial of H, x1, x2, x3. And then I have the second term where first the H and then a partial x1, x2, x3. So these terms are not 0, but the claim is that they can be fixed by introducing an appropriate 3 bracket. So these are fixed in the sense of becoming part of an L-infinity algebra by defining an appropriate 3 bracket. So this is a B3, x1 bar, x2 bar, x3 bar, which is given by minus P bracket H of x1, x2, x3, plus 2 terms, so plus the obvious symmetrization. So first we can check that the degree counting works out. So B3 is supposed to have degree -1. H has degree +1, but I have two nested brackets here, each of degree -1. So it becomes out to have overall intrinsic degree -1. So that's nice. So that shows you already that just for degree reasons, you could not write the natural answers for the 3 bracket unless you have an extra map to play with, like this homotopy map H. So just writing a nested bracket in terms of the original bracket wouldn't do. But the claim is that this does the job. And I mean, I won't prove it in all glory, but you can structurally quickly see that it works. So let's act as the differential on x bar on this object. So this is, as you may recall, one of the terms of the L-infinity relation with 3 arguments. Now, I assumed at the beginning that the projection and the differentials are compatible in the sense that I have this relation here. So I can move the differential past the P. So now I have a differential acting on this whole object here. And here, of course, I can do more. Now I know I have the DJLA relations on X, so I can actually move differential inside. So I get a term P of a bracket del H on X1, X2. Of course, I also get more. I get a term with X on the second factor. So I have to take care of this eventually. But here you see already you naturally produce the structure that came out here from the commutator. And similarly, in the L-infinity relation, you also have terms of this type, B3, acting on del bar x1 bar, x bar 2, x bar 3. And if you use the general formula, that means you have to put here a dx1, x2, x3 plus ... And now you can use again the L-infinity relation. So here you can move out the partial acting on x1, x2. Of course, minus the correction term with the partial is on the x2. So you have to verify that all these extra terms eventually cancel in the full equation. But you see that structurally you produce exactly the contributions that came from the Jacobiator. And in fact, it's a nice exercise to verify that this fixes the L-infinity relation. Okay, are there any questions on this part?
Yeah, Olaf, I have a general question.
Yeah.
Which is, suppose we are given an L-infinity algebra, and we want to see if it's possible to lift it to a DGLA, to a bigger space.
Yeah.
Can one see if there is any obstruction? I mean, is there a systematic way to study this?
Yeah, that's of course the most interesting direction. The other way around. So if you have something very complicated that's given by an L-infinity algebra, can you make it simpler by going on a larger space? And I believe that there are mathematical theorems that basically tell you that that exists, but that they are the sort of high level of obstruction where they're not really particularly useful for what we are doing. Now, if there's some expert in the audience who wants to correct me or clarify this point, please speak up, or maybe in the discussion session. So the short answer is I believe there are such theorems, but I have not yet seen a version that seemed particularly useful for the kind of thing we would like.
I see. Because that would give what we call cubic string field theory, right? Cubic closed string field theory, if there is a general result like that.
Yes. Right. So I think that should exist according to mathematicians, except that the theorems they have are either not constructive or, well, not constructive in a useful sense, I guess. I mean, you could ask a similar question already for simpler theories like general relativity, right? That is given by a very complicated L-infinity algebra. If you just take the perturbative expansion of Einstein-Hilbert, but that should be writable as something simpler, differential graded Lie algebra, so just the cubic theory. And for GR, in fact, we know how to do that. You just introduce suitable auxiliary field, and you can actually make it cubic. But I'm not aware of sort of an L-infinity construction that really usefully would give you that directly, as opposed to an abstract statement that it should exist.
Yeah, the point is, if you do it in string theory, I mean, it will probably also tell you how to quantize it, because in string theory, we know how the usual L-infinity algebra is quantized, right? I mean, you just lift it to quantum version of the algebra.
Yeah.
And so if you could really do this, maybe perhaps one can get a cubic theory that can be quantized without any problem. I don't know.
Well, but with the analogy with general relativity, I would think they have nothing to do with each other, because that you can make general relativity cubic doesn't mean you can now quantize it. Or does it? Perhaps?
Yeah, but the point is general relativity you cannot quantize anyway, right? Because you have these UV problems and so on.
Yes. Okay.
But that probably will not have to worry about in string theory.
Yeah, that's right.
Okay, thank you.
Okay, thanks for the question. So this was just an illustration of for the 3 bracket, but you can one can prove this to all orders. And of course, in order to actually prove that, you have to use these more efficient formulation in terms of co-derivations. So you can prove this, what's called the homotopy transfer theorem, or related to what's called the perturbation lemma, in terms of co-derivations. So if you start out with the co-derivation on X, so now I assume that it's a full-fledged L-infinity algebra. That was just for illustrative purposes that I said, let's take it to be a DJLA. So I can write it in this form. I split out the leading term, the differential, and then I have an infinite series of higher maps or co-derivations. And that squares to 0. Now the claim is that the appropriate co-derivation, and hence L-infinity algebra on X bar, is given by this, where B bar is given by the projection of B plus BHB. So it's an infinite series, and it has this geometric series-like structure. So if you want, you can write it more concisely as a geometric series, for instance, like this. But the important point is that for any fixed bracket of degree n, only a finite number of terms matter here. So only a finite number of actions of B or HB is actually non-zero. So this formula is totally well defined. You don't have to worry about convergence conditions or anything like that. And so you can prove that this then squares to 0. And in fact, you can also prove that this is a co-derivation. Now, there are various technical complications involved here, all related to the fact that you have to find a proper uplift of this homotopy map to the full tensor, symmetric tensor algebra. So that's a complicated story, and usually is done by means of extra conditions, side conditions that are not really part of the problem. But the upshot is there's an uplift of the action of this homotopy map that entered this basic relation up here in such a way that this homotopy relation holds as a map on the entire symmetric algebra. And then once you have established that, then it's very easy to verify that this new co-derivation is given here indeed has all the required properties. And so defines an L-infinity algebra on X bar, the smaller space. Okay, so there's also some sort of graphical representation of these brackets and operations, which some people like. So let me just briefly mention that, which especially for physicists is nice because it establishes a connection with the Feynman rules in field theory. So this graphical representation is very simple. You just encode the brackets, let's say the 2 bracket, as a graph like this. So you want to take 2 inputs, x1 and x2, and you get 1 output, which is the bracket. And you just denote it by this graph where you have 2 lines for the inputs and 1 line for the output. And similarly for all higher brackets. So if you have 3 inputs and 1 output, that defines the 3 bracket, etc. And then you can have fun with drawing pictures that represent the Jacobi identity if you have a Lie algebra and such things. Now I don't want to get too much into this. Just to let me say that the differential and this homotopy map play a natural role here. So you can think of an action of the differential, let's say on this basic graph denoting a 2 bracket, by just defining it to move through the 3 parts of the graph. So I have a dx1, I have the d here, can have the d on the second one, and I can have the d on the output. And if you remember the basic Jacobi identity, if I choose the signs here correctly, then this is just 0. So by Jacobi identity, I should say the Leibniz relation, that's part of the generalized Jacobi identities of L-infinity algebras. Okay. So the reason this is sort of cute for what we have in mind in field theory is that if I now want to look at the 3 bracket that comes from homotopy transfer, I can draw it as follows. So I have a 3 bracket, so 3 inputs. And let's look at the formula again. The formula is here. It may look a little convoluted. No, it's not so convoluted, but some people may prefer it in graphical notation. So what we're doing here is we take the bracket x1 with x2 here. Then we act with an H, the homotopy map, and then we take another bracket, and at the end we project. So if you draw a little picture, you could draw it like this, where you first start with x1 and x2, let's say, take the 2 bracket, and now you let it act on it with H. And then you take another 2 bracket with the final argument to get an x3. So that's what effectively homotopy transfer tells you is the 3 bracket. And then you have 2 more terms as in the homotopy transfer relation. And if you look at this picture and you twist it a little bit, so you rotate it around, it looks sort of like a Feynman diagram, like this or like this, where the H plays the role of the propagator. And that's indeed not just an analogy. In fact, in many or most or all, depending on your point of view, field theory applications, that's the role of the homotopy map. It's the propagator. Okay, so that's perhaps a little sketchy. So what I want to do for the rest of this lecture is to illustrate this homotopy transfer in terms of a very simple example. In fact, I will go back to the scalar example that we had at the beginning of the lecture. And I make it even simpler by restricting to 0 dimensions. Unless there are any questions before that. Okay. If not, then let me start with this model. So I want to look at the 0D, 0-dimensional scalar toy model. So the basic variable I consider is a vector phi I. Is the vector in Rn. So I runs from 1 to n. And I consider an action that looks as follows. So you have the quadratic term. Well, it's always the same story. You start with a quadratic term, then you put a cubic term, and then you keep going. But here, actually, I want to stop for the explicit discussion at the cubic level. But it doesn't really matter too much. So you could continue for, for a while. And now you've seen it so many times, so you know how the chain complex works. So x0 is just this vector space Rn, where the phi I lives. And this is mapped onto x-1, which for notational reasons, at least, I want to think of as the dual to Rn. And that's, of course, the differential is defined as before, just by the quadratic piece of the action or of the equations of motion. So this I denote here by lower index I, because it goes sort of to the dual space, the space of equations of motion. You can think of as the dual space, and that action is just given by the matrix Aij. So here the differential is just the contraction with this matrix Aij, and the 2 bracket phi 1, phi 2 is the 2 elements in x0, again lands in x-1, indicated by a lower index, and that's given by lambda Aijk phi j phi k. And of course, I assume all these Aijk to be symmetric. And then potentially, if you have higher order terms, there are higher order brackets, which are just exactly of that form. You have some coefficients, I1 to IN-1 for the, or n+1 for the n bracket. And you have this obvious expression. And that, of course, trivially as defines an L-infinity algebra, as we discussed initially. Okay, and now I want to do the following. I want to split the fields into 2 subsets, and I want to integrate out one set of fields. And I will show that this integrating out at tree level is precisely what homotopy transfer does for you. So we split the fields as follows. So I write the phi I, the vector phi I, as a set of components phi I bar. So this I bar runs from some subset of indices. And the corresponding components I label by U. So I call this chi U, where U runs over the remaining values. So now I want to do homotopy transfer to the smaller space of phi I bar by getting rid of chi I, and I want to illustrate that this is in field theory language the same as integrating out chi. Okay, so let's see how this works. So let me make a simplifying technical assumption, which is that this kinetic matrix Aij has a nice form for this decomposition. So it's just block diagonal with respect to this decomposition.
Integrating out at the quantum level or at the
no, at the classical level, meaning at tree level, or meaning using the equations of motion. But I will show what exactly homotopy transfer does, and what is then the appropriate notion of integrating out. Okay, so going back to this homotopy relation, so we have to define a couple of things. We have to specify what's the projection, what's the inclusion, and we have to establish if there's a homotopy map that makes this relation work. Okay, so the projection of phi and chi is just equal to phi. That's the intuition we have. We want to project to the subspace of the phis, and correspondingly the inclusion, which goes the other direction, so that has phi as an input, is just, well, the only thing you can put is phi comma 0. So the homotopy relation compares iota p to the identity. So let us work out iota p minus the identity, acting on a general vector phi and chi. Okay, so this is simple. So the p just projects it to phi. The iota then makes a phi comma 0 out of it. And then I subtract minus phi chi. So the phi goes away, and I just get 0 minus chi.
Yeah,
So
Olaf?
Yes?
Yeah, in the definition of the inclusion, you could have introduced some multiple of phi in the second part, right?
Yes.
It didn't have to be phi comma 0.
Right. So in some applications, you actually do something like this, where you so this in this example is literally a projection. So you say you have a space, you have a vector, and just throw away a bunch of components. And then what the inclusion does is that it takes a vector of the truncate of the projected space and views it as a vector of the larger space. So that's then what the inclusion does here. But you can in fact do the more general things where the inclusion is not, this iota is not literally inclusion in that sense, but where you have a more complicated embedding of what is called phi here in the larger space. And it depends on what kind of, it depends on the details, how you want to obey the homotopy relation. So it's a good and important point, but just for this example here, I do the simplest thing just to illustrate what's going on.
Okay, thank you.
Okay. So this is what we get, and this is supposed to be equal to partial h plus h partial acting on phi chi. So we're supposed to find an h so that this is true. Now the first h, the first term here, actually we can see this is not going to enter because h is a degree +1 map, so it goes in the opposite direction of the differential and it's acting on fields. So if you go back to the complex here, that since everything to the left is trivial and everything to the right is trivial, there can only be one non-trivial h, which is going from x minus 1 to x0, so it's the h minus 1. So any h we would try to define here, so this is an h0 acting on fields, must be 0, must be trivial. And that's precisely what's true for the first h here. It's an h acting on fields, so that is just must be 0 because there's no space where this could go to. Okay, so that means, sorry, are you still there?
Yes.
Okay, sorry, I just swiped the wrong direction. Okay, so I have only the second term. So this is an H acting on the differential, acting on the vector. Now the differential, remember, was given here. It's just the action of the matrix A. And since I take this matrix A to be block diagonal, I have something like this. So I have an A, I bar, J bar, phi, J bar, and A, U, V, chi, V. And this is supposed to be equal to minus chi. Sorry, 0 in the first component and minus chi in the second component. And so that I can just obey by defining H to be sort of this operator that does nothing except in the chi block, it is the inverse to A. To the inverse here, I mean the inverse to the matrix AUV that defines this block here. Yeah, you can see that this works because if I act, so this matrix will clearly give 0 on the first component. On the second component, the A's will cancel and have a minus chi, and this is precisely what I should get. So the claim is that is a good homotopy. It satisfies the homotopy relation. So now I can just apply the machinery of homotopy transfer. And I think I should even finish in time. So, well, first, the trivial part is the transported 2 bracket. Not much interesting is happening here. So I just write it out. So the 2 bracket on the projected space, I write like this. So we have now, it takes values in something with an index I bar because it lives in the projected space. The 2 bracket of the full theory was defined by this ijk numbers, but now everything gets projected. So phi 1 is projected, phi 2 is projected. That was the general prescription. So this is also projected, and at the end I still project, which is the general formula we had up here. Right. So this is just the prescription. You take the projected vectors, you uplift, and then you project at the end. So this is what this formula does. So that's not so interesting. What is more interesting is what happens to the 3 bracket. And so in fact, you see that since we started out by looking only at a cubic theory, if there's now a non-trivial 3 bracket, that means a quartic interaction will appear. And that's, of course, what you would expect upon integrating out degrees of freedom. Okay, so let's look at the formula we had above. So we have the 3 bracket on phi 1, phi 2, phi 3. Let me just recall the general formula. So I have the projection, the bracket of H acting on phi 1, phi 2, phi 3, and then plus 2 terms. And well, let me work out what this is. So let me just put here an index I bar, because everything is projected at the end. So again, it lives in the space of equations of motion, so it carries naturally a lower index that is barred because it's projected. Okay, so let's work out first the outer 2 bracket. So just for your help, let me recall the 2 bracket of the bigger space. Phi 1, phi 2 was just lambda aijk phi 1j phi 2k. So now here I first write out the outer bracket. So this is equal to lambda times I bar j k h acting on bracket phi 1 phi 2, having an output j, and then phi 3 K. Now, all this is already supposed to be projected, so I can put here a bar immediately. And now let me work out the second bracket. So this is equal to lambda A I J K H J L. Now I do the second bracket, A lambda A L M N. Now everything is projected because the phi's are assumed to be projected. That was part of the prescription. And the final step is to use this homotopy map here, which is only non-trivial of this UV block down here. So that first of all gives me a minus sign. Bring the lambdas together. So this minus lambda squared A I bar K bar, and then the J becomes a U. And then I have the A minus 1 that defines the H, UV times A. And remember, all the A's are fully symmetric. So the order of indices doesn't matter. Phi 1 M, Phi 2 N bar, Phi 3 K bar. Okay. So, and here we always had the plus 2 terms. And you can convince yourself that the effect of these extra terms is just to make this totally symmetric. So the final result is actually is a factor of 3 and now symmetrized over M and K in this case, something like this. Okay, so this is the 3 bracket following from homotopy transfer. And you see, if you look at these formula more carefully, this is basically exactly the kind of structure we get from Feynman rules, where you have cubic vertices, given here by the A with 3 indices, joined by a propagator, which is the inverse of the kinetic operator, so the A minus 1. So the structure is exactly like normal Feynman rules. And just to complete the story, this is the same as integrating out classically chi classically or at tree level. Because what does it mean to integrate something out classically? It just means you solve the equations of motion perturbatively and reinsert. So if you look at the original equation of motion and specialize to the chi part, it looks something like this. You had the linear piece with A, the matrix A, and then you had this interaction piece, which links chi to the phi's that you keep, the phi with Barton indices. And then the leading part of the equation looks like this. So you solve for chi in terms of the phi's. So to leading order and lambda, the coupling constant, this is just given by A minus 1 UV AB IJ, let's say phi I phi J. So you have chi in terms of 2 phi's. And if you plug this back into the action, you generate a quartic term, a new quartic term that wasn't there before, which is something like minus lambda squared over 8 A I J U A minus 1 U V A B K L. And now I have 4 phi's, phi I, phi J, phi K, phi L. And if you read from this, according to the general dictionary, the 3 bracket, you get, of course, exactly the same, the 3 bracket that homotopy transfer gives you. It's the same structure and it's the same story. So that's the most direct physical interpretation of homotopy transfer. at the L-infinity algebra level, which covers classical or tree-level field theories, it implements the integrating out of degrees of freedom. Now, the example which we used here is very simple because there's no gauge symmetry in the game. And as I reviewed at the beginning, all the L-infinity relations are in fact trivial. So these examples are not so interesting. But the nice thing about homotopy transfer is that it works also for gauge theories. So if you look at the way we solved here the homotopy relation, it was sort of quite trivial because the differential was given by an invertible operation, this matrix A, and then this equation is just solved by declaring H to be the invertible of that guy. Now, if you have a gauge theory, of course, the kinetic operator is not invertible precisely because of the gauge symmetry. But you also have this extra term in the homotopy relation that didn't play a role here. It didn't play a role precisely because there's no gauge symmetry and hence no extra space to the left to the space of fields. So in fact, what can be done is that you can define homotopy transfer also for gauge theories without necessarily having to fix a gauge explicitly. And that's in fact something my student Alison will talk about on Friday. That's another project with her and my postdoc Christoph Chiafrino, where we use the language of L-infinity algebras, homotopy transfer, etc., to find an effective procedure to define gauge invariant variables in cosmological perturbation theory, where the basic mechanism that is used is much more subtle than this example I had here. But I think I'm almost exactly 1 hour, so I think this could be a good time to stop.
Thanks a lot, Olaf. So from everyone, we thank you for that 3 lectures. It was really interesting. So I suggest that now we take a small break of 5-10 minutes, and so I don't know if you are free for the discussion. So in any case, the Zoom will stay open until 11:10 when we get Barton to give the next lecture. But you are free to stay in the room, discuss, and if Olaf is here, ask questions. Otherwise, we'll have a question and answer session this evening.
Yes,
later, depending on your time.
Yeah, I will be there, so we can definitely discuss.
Okay, so you can ask Olaf whenever you want. Thanks again, Olaf.
Barton, please go ahead.
All right. We started, it says internet connection is unstable. I hope it will be okay. Just let me know through the chat, maybe, if any.
So far, it's fine. The video and the voice seem to be working well.
Okay. Very good. I have my chat open just in case suddenly I don't get to be heard. So we were talking last time about these moduli spaces and Teichmuller spaces of surfaces. So we think of S as a topological surface and has genus G, and it has n boundaries. And on that, we put a hyperbolic metric with geodesic boundaries. And there's many hyperbolic metrics that you can put. And in particular, the lengths of the boundaries vary on the various hyperbolic metrics. So that space is much too big. We called it tau, Teichmuller space Gn of S. It's not quite the one here. This one is the one that is more interesting for us. Is it a Teichmuller space of genus G, n boundaries, but every boundary fixed to have be a geodesic of length L. By that time, this Teichmuller space is becoming the size that we want. That is, it has the dimension of MGN as well. So this is a moduli space of Riemann surfaces with boundaries that happens to have the same dimension of the moduli space of Riemann surfaces with punctures. And of course, there's a desire of trying to relate the two. Now, while in hyperbolic metrics, there's been enormous progress in constructing them in a nice way. So now we're going to go on, and it's all based on Teichmuller spaces. You certainly, at the end of the day, we really want to figure out what is the moduli space of those surfaces, N, L. So it's the Teichmuller space of G, N, L of S, and the mapping class group of S. So this is the moduli space of hyperbolic metrics. Space of hyperbolic metrics. So now there is a natural question, as we were saying, how do you turn this moduli space of hyperbolic metrics on surfaces with boundaries? How do we make it strictly into a moduli space of surfaces with punctures? So, all right, well, there has to be some way to do it, and you basically have to cap the boundaries, put a cap. So the natural way to put a cap is to glue a disk, a unit disk, with a puncture at z equals 0, and you glue the boundary of that unit disk, parameterized by an angle theta in that z coordinate, glue it with the boundary of the hyperbolic surface, parameterized by length. So you just glue it together, and the disk with its puncture produces a puncture. So there's a canonical way of doing that. And if we think in terms of metrics, the simplest way of doing that is to imagine that each time you have a boundary on the hyperbolic metric, what you're going to do is attach a semi-infinite cylinder which is conformally equivalent to a punctured disk. And a semi-infinite cylinder has a picture of a metric with zero curvature. Here you have k equals -1. That is the surface. The surface is here with k equals -1, but there's this piece that you associate with the puncture where you add this quantity. So once you have that, and you do that on any boundary of the Riemann surface, you have a map. And which map do you have? You have a map G for grafting. Mathematicians like that word, grafting cylinders. Grafting an infinite cylinder, and they put a prime, and it maps M, G, N, L. So any surface in the moduli space of surfaces with n boundaries of length L, it maps it to P hat Gn. Because not only you've created a puncture, but you've created a cylinder that defines a canonical coordinate in the surface with the cylinder attached to it. This curve that you have here is the coordinate curve. It's the boundary of the cylinder, is that curve that we draw around the punctures. The puncture here is far at infinity over here. And therefore we have a map like this. And the surface, if we are putting metrics on it, now if we put an annulus, a hyperbolic annulus, the surface would flare up. So it's kind of a strange thing. So it's very natural to put in here this flat metric. Now, of course, now the surface becomes a mix between hyperbolic and flat, but maybe it's not so strange. So finally, you can compose with G to GR prime infinity, you can compose the forgetting map about local coordinates, and this is the map GR infinity, and this map takes again MGN L. Well, it would take it first to P hat GN via the GR prime infinity, but then forgetting, you get to MGN. So we have a picture of this thing in which you have MGN-L that had the same dimension, we just discussed that, of MGN, but now you have a map, and here is the key theorem in this subject, for which we probably have a little bit of intuition. Mondello, an Italian mathematician. Mondello, 2011, which proved that GR is a homeomorphism. Homeomorphism means one-to-one. It's as good as it gets, one-to-one ontomap. So the upshot of that theorem, which is a crucial theorem, is that if you have MGN here, and you have PGN, P hat GN, and you have here, there's this section which is GR prime of M, G, and L. So basically, what we were saying is, if you take the Riemann surfaces with boundaries and equal boundaries of length L, this map is the one that just attaches the cylinders. Then you get a surface in PGN. And if you forget about the cylinders, if you forget about the local coordinates, you project down to MGN, and it's a homeomorphism. So the projection map here, the projection map is one-to-one. So one-to-one gets projected. So basically what you get from here is that you will cover moduli space. So if you consider the moduli space of the surfaces with boundaries and you attach cylinders, you are producing a section over P hat GN. So this is a section over P hat GN. And this section has represented, so we could call it the hyperbolic section, a hyperbolic section, because it's represented by surfaces with hyperbolic metrics and cylinders attached at the boundaries. But every surface there, if you forget about the cylinders, is perfectly hyperbolic. Now, if it's perfectly hyperbolic, there is the question of how they're going to look. And these surfaces are going to look in the middle of the moduli space. In the middle of the moduli space here, they're going to look quite regular. the closed geodesics are going to be of finite size, but when you go to the boundary, they're going to have closed geodesics that are becoming very tiny. And that's the degenerations where you start approaching the noded surfaces. So even though the boundaries are always kept at length L, and L is a number that you choose, as you move in this section, you reach surfaces in which inside the hyperbolic center of the surface is really hyperbolic except for the cylinders. Inside that hyperbolic surface, you're going to find short curves, and that's unavoidable, which suggests that this section is not the section of the full string field theory amplitude, but rather an auxiliary section. And what we're going to try to find out is how to produce in here. Let me do here. How to produce in here a piece. That's probably too light to be seen. A piece that we're going to call nu GN. So a piece nu GN is all what we want, because in general, we want the generations to be produced by the Feynman diagrams. We're trying to do a field theory. So only a piece of this section is going to be used for the string field theory vertices. And so that's our aim at this moment, to determine that piece. So it's a good moment if there are questions on what we're trying to do. That would be a good point to stop.
Barton, may I ask a question?
Yeah, Eugene.
So, can you describe this section in terms of hyperbolic geometry by conformal transformation from the local coordinates, as usual? In principle.
In principle, yes, absolutely. So
in practice?
Sorry, in practice, explicit formulas for the conformal maps are not known in general, but there was a paper by Atakan Firat, a graduate student at MIT, who's speaking tomorrow on a different subject, that he discusses how to find the local coordinates associated to the hyperbolic vertex in detail. It's funny that the mathematicians haven't quite focused on this problem, but I will say a couple of words about it. Yeah.
Thank you, Barton.
Sure. Any other question? Okay. So what we need now, it's a very beautiful property of hyperbolic geometry regarding what is called Color theorems. Color theorems. So there's something called the color C. I've been using last time C for chains, but now forget about chains. Color of a geodesic gamma. And this is the width of the color, width. So basically, if you have a hyperbolic surface and geodesic gamma, the one thing about the hyperbolic surfaces is that they're not foliated by geodesics. There's geodesics in disjoint geodesics, and there are discrete number of geodesics. You can sort of count the geodesics on a hyperbolic surface. Suppose you have a geodesic, the color represents the piece of the surface. I wanted to use a different color. the piece of the surface that contains points, all of which are at most a distance W/2 from the geodesic. So the color has width W, and any point in the color, any point P, must have a distance to the geodesic, the shortest distance to a geodesic. That's something you can calculate in hyperbolic geometry. Figure out the shortest distance from a point to a curve. That distance must be less than or equal than omega/2, and that produces a color. So the idea in the color theorem is that there's a way to establish a correlation between the width of a color and the geodesic that defines the color. So depending on the length of that geodesic, you can establish a canonical color. So given a length, there's a canonical width for that length. And the beauty of that thing is that that canonical width ensures something nice about the surface, as we will see in a second. So we correlate the width to the geodesic length, and then if you have disjoint geodesics on the surface, you know, geodesics might intersect, but in general, suppose they don't intersect, then they're totally disjoint and they're fixed geodesics. If you correlate properly the width of the color to the length of the geodesic by a formula, you can guarantee that the colors are also disjoint. So if you were asking the question, you have a set of geodesics, what is the maximal disjoint thing that you can thicken the geodesic into a little cylinder? That is answered by the color theorem. So the theorem says,
Barton, so this requires that the geodesics never intersect?
It must be a simple geodesic, yes. Is that what you were asking?
Yeah, yeah. What is a simple geodesic?
A geodesic without self-intersections.
No, I'm not asking that. I'm asking that suppose there is another geodesic that intersects gamma.
Yes.
That's not possible in hyperbolic geometry.
That's possible, yes, absolutely.
But then the colors will intersect, right? Colors of these two geodesics.
That's right. The colors will intersect, but the theorem says that if the geodesics don't intersect, these are the fattest colors that you can always assure that the colors don't intersect.
I see. Okay. Thank you.
Okay. So, so basically, here is a theorem. I'm restating it. Choose a collection of gamma I of disjoint, simple, closed geodesics of length Li on the surface sigma. If the width Wi, well, let me write it in word, the widths Wi are given by sinh Wi/2 sinh Li/2 equal 1, the colors C of gamma I Wi are disjoint in sigma. There's a wonderful book in hyperbolic geometry. I highly recommend it, by Busser. I think the PDF is available free online, and somebody can put the link maybe in the chat. And the book is not expensive. It's $30–40, and it's really readable. Lots of pictures and and fairly nice. And all these theorems are written very explicitly there. So, so that says this thing, they're inversely correlated. If the length of a geodesic is small, so if the geodesic is very small, there's a large cube and the width can be quite large. On the other hand, if the geodesic is very large, the color is very thin. So here it is, that's the theorem. And you know, we can picture this inequality, and it's kind of nice. You can picture the graph here, an L, N-E-L-I, and a W-I. And this curve represented by this equation is a curve that looks like this. Almost like a hyperbola, but it's not a hyperbola. But it kind of looks like that. It's sort of hyperbolic in some way. Anyway, it's inversely proportional, and there's a particular number here that makes for a special point where you call this L star, that the width of the color is exactly equal to the length of the geodesic. That L star is the length that satisfies this equation. So you would have sinh of L star over 2 squared is equal to 1. And that means that the sinh of L star over 2 is equal to 1. And L star is 2 arc sinh 1, which is the number, you can write it with square roots, I will not bother. It's about 1.76275. And what does that L guarantee? Is that for L less than L star, W will be greater than L star. So remember, if you choose an L, the smaller the L, the larger the W. So when you go through that critical point, L star, in which the W, the width and the length are the same, for that, for any length smaller than L star, the width will be greater than L star. So now there's a couple of corollaries that make it easy to work with this. The first corollary that needs a little bit of a proof, but it's also in Buser. It talks about the geodesics that, in a sense, Ashok was talking about that intersect. So suppose you have a simple closed geodesic gamma of length L gamma, and it intersects another geodesic delta, not necessarily simple, so that delta is not necessarily a simple geodesic. Yeah, that Harold posted the book in the chat. Not necessarily simple, of length L delta, and now very much related to sort of the to the Color Theorem, you have an inequality this time that sinh of L gamma over 2 times sinh of L delta over 2 must be greater or equal than 1. So basically, I think intuitively, this is telling you that any other simple closed geodesic that intersects gamma must travel through the color. It just cannot be that it just begins on one side, goes, hits gamma, and returns. There's nothing to hold that geodesic. You could contrast. So in order to get it to work, you really must travel through the whole color. And if you travel through the whole color, you must be longer than the width, which is determined by a similar equation, that equation on top here. So being greater than the width guarantees that. One final encapsulation of this statement. So this is a simple intuitive corollary, and now we can phrase it in another word. Maybe it's a nice way, and I'll phrase it like this. A simple geodesic is closed, of course. All these geodesics are closed. Geodesic of length L less than L star cannot intersect another geodesic of length less than L star. So I'll box this and just say a word again. So we had this corollary was about intersecting geodesics, and now we apply this thing, this corollary of intersecting geodesics. The intersecting geodesics says that the geodesic that intersects gamma must be longer than the color. So if you have a geodesic to begin with, this gamma that is less than L star of length, its width is bigger than L star of length, and therefore any curve that intersects that geodesic that is smaller than L star must be larger than L star. So that is a conclusion, the most important conclusion of this. Okay, we got the hyperbolic geometry there, and now we can define the hyperbolic vertex and then go ahead and prove that they work. Hyperbolic string vertices. For that, we need one more definition, which is what is the systole of a surface? Systole of a surface with a metric. And this is the length of the shortest non-contractible geodesic. Length of the shortest non-contractible geodesic. And if the surface has boundaries, we also say not homotopic to the boundaries. Because those boundaries are kept at fixed length. We always keep them at fixed length. So those are not interesting curves. So the systole of a surface, a hyperbolic surface, is the shortest geodesic that you can find. If you have boundaries, it's still the shortest geodesic you can find, and doesn't mean it's equal to L, but maybe there's a short geodesic of length exactly L inside the surface, but that's the systole. So basically, here is the vertex now. Remember, we had this MGN, and then we had this section that was the appended cylinders on the moduli space of Riemann surface G and L. So once you have that, we're trying to find the new GN of L, and of course the question is the L has not been fixed yet. It will be fixed soon. And so how are we going to define the new GL of N? Well, I mentioned before that all these surfaces in that section have cylinders of length L, but inside they're purely hyperbolic surfaces, and when they approach degeneration, a curve becomes very little and the systole becomes very little. So basically the answer or the conjecture for the hyperbolic vertex that we prove now that it will work is based on saying, okay, pick those surfaces where the systole is greater or equal than L. Not L, but greater or equal than L. So here it is. Let me write it. Nu GNL is defined as the set of surfaces in GR infinity prime M G N L such that the systole of sigma is greater than or equal to L. So there may be surfaces in the middle of the moduli space, in the center, where the boundaries have length L, but the shortest curve inside might be 3L or 4L or something like that. In fact, those numbers mathematicians calculate them. And for genus 2, the exact number is well known, is famous, and the systole of those surfaces. And it's a whole industry of people computing lengths of geodesics. Because if you actually start, the beauty of this subject is that when you start counting geodesics, including self-intersections, the number of geodesics as a function of L, the length of the geodesic, grows almost in a similar way as the number of prime numbers grow. So it's kind of a fascinating subject. So basically this says, pick the surfaces with no geodesics shorter than L. So that's the vertex. And the little theorem that we need to show or claim is that nu GNL solves the geometric master equation that we wrote last time if L is less than L star. So as long as you choose L less than L star, where L star was this number, 2 arc sinh 1, you get a string field theory, a solution of the master equation. So I'm going to try.
Just a curiosity. If so, you have an infinite number of L, all the L less than L star are good. So these different vertices are associated with the field redefinitions?
Yes, this would correspond to different ways of cutting the moduli space. In the questions yesterday, Sen was saying if L is very small, the vertices cover more and more, because remember, as you approach infinity or degeneration, the systole is becoming smaller. So if you require the systole to be very small, you get most of the moduli space, and these are related by field redefinitions. in terms of the geometric master equation, they're related by canonical transformations generated by the anti-bracket of Riemann surfaces. Yes, these are equivalent string field theories. You might think either the most useful string field theory is the one with it's equal L equal L star, or maybe the one in the limit as L goes to 0.
Thanks a lot.
Sure. Okay, so let me discuss the proof of this thing. So we have the geometric master equation is minus h delta nu minus 1/2 nu nu. Since this is a lecture, so I think doing the proof is kind of interesting. If this would be a normal talk, you would go say, okay, it can be proven, let's move on. I think we want to understand a little better why it happens, and it's a nice thing. So here's a left-hand side, and here's the right-hand side, and you want to see that these two things are the same. So I'm going to try to show that every surface that is in the left-hand side is on the right-hand side, and then every surface that is on the right-hand side is also on the left-hand side. So let's do the first one, which would be left-hand side is inside the right-hand side. Let's try to prove that. Okay, so if you have a surface that is on the left-hand side, is on the boundary of the vertex region. The vertex region is characterized by the length condition that the systole reaches value L that you choose. It has to be less than L star, but the value L. So the boundary of this thing is when one geodesic, an interior geodesic, reaches the length of the systole. And that is the boundary. If more than one geodesic reaches a lower codimension boundary, but it's not just the standard boundary. So let's assume one geodesic reaches the thing, and it has to be a simple geodesic, in fact, because in a hyperbolic geometry, the shortest simple closed geodesic is shorter than the shortest non-simple geodesic. So all these things have been proven. So there's nothing weird happening. And it must be a simple closed geodesic that reaches the value L. So imagine that you see now, here's the big blob of a certain one geodesic that reaches the length L. So one simple closed geodesic reach length L. And then we can imagine cutting along this geodesic gamma to get a surface called S cut. Now, if S cut, you cut along, is disconnected, we claim that each piece is a surface in a vertex, because on each piece, there is all the geodesics are bigger than the value L of the systole. So it is part of the vertex. And on the other surface that you've cut, all the geodesics must be bigger than the value L, because otherwise the big surface before you cut it would have had another geodesic that is too short. So these two things that you cut must be two vertices, and therefore the surface in this case arises from this term, in which you glue two geodesics, two surfaces across a boundary. Similarly, if you're cutting along gamma and the surface doesn't fall apart, it now has two boundaries, and it's two more boundaries because you've cut, and there's no curve in this surface that is too short, because otherwise it would still be too short when you glue it again. So this surface must now be in a vertex, and therefore it gives you back the original surface by applying this operation. So in this case, it shows that any surface that has reached length L must have arisen from either of these two terms, and therefore it is on the right-hand side. So that is the end of this proof of this side, which is the kind of trivial, simple part of the proof. Now we need to do the right-hand side inside the left-hand side. So let's do it this a little slow, because that takes a little more thinking. Here we have, suppose the surface comes from the right-hand side. You have a surface S1 and a surface S2, and you glue them together, and each one is in a vertex. You glue them together through this curve gamma. And so we're trying to consider the right-hand side. So we have this case, we're gluing two surfaces, each one on a vertex, and you have gamma. And gamma has length L. Remember, length of gamma is equal to L and is less than L star. Now the question is, if this is a surface in the boundary of nu. So for that, well, one curve has reached the critical length. So this is fine. In the boundary of nu, there must be this. But if it's in the boundary of nu, there must be no other short curve. And we know there are no short curves on the right, nor short curves on the left. The only thing that we need to show is that there are no short curves that are neither on the left nor on the right fully. And that is, there's no short curve that somehow it's in both of them and just tries to go this way. Well, we have a sledgehammer for this proof, is our claim. A simple closed geodesic of length L less than L star cannot intersect another geodesic of length less than L star. So this closed geodesic, the blue one, cannot intersect another geodesic of length less than L star. So there's no way the red geodesic could be smaller than L, because it even cannot be smaller than L star. The color is too big. There's no way this can happen. So that takes care that there's no geodesic that can do that. On the other hand, this proof can be strengthened quite a bit in an interesting way. But let me do the other case first, the case where you have delta S. I'm sorry, I should do blue. You have delta S, you have a single surface, you do delta, and so you have a single surface with two boundaries, you glue them across the boundary, and let's put another few more genus here. Sorry. This should be like this, and I think I'm not drawing it very well. And here I have Oops. No, this has to be deleted. And then I have this. And, yeah. So here you have a surface that has been glued in delta of S. So this curve has length L here. It's a closed geodesic because you glued two things in the surface to form this handle. And now again, you've created a more complicated surface that any closed curve that was in the surface that was open is good, is long enough, because this surface is in a vertex. On the other hand, the possibility that you've closed implies that now there are new curves that could become short or could be short, but those curves have to cross here and then do something. And this is again the theorem. If you have a curve that has length less than L star, which is our case because we choose L equal less than L star, no intersecting curve have length less than L star. So all these red curves are long as well. Therefore, the systole remains L or bigger than L, and there's no problem here. So basically, the colors have established for us that we always solve the master equation. I want to add, I don't have too much time, but I want to add one more comment here, is that in the first case, when we were doing this, the proof can be done a little better, and it doesn't require the Color Theorem. That has an important implication. Let me review that proof. So here we have a geodesic of length a systole here, A1 and A2, and we're worried about curves that may be, curves that may intersect this one and may be short. So let's draw these curves as maybe this color. So the problem is a red curve that it could be too short, while this other, when you glue together these two surfaces. So let's call this L1. L1 and L2, the lengths of the two pieces of the geodesic that are on the side. This one, however, has length L, and call these pieces that get cut here A1 and A2. So this thing is problematic if L1 plus L2 is less than L. This is problematic because this geodesic is just far too short. On the other hand, A1 plus A2 plus A2 is equal to L, because that is the gluing geodesic. So first, from this quantity, L1 plus L2 less than L, there must be one L, either L1 or L2, and Li that is smaller than L over 2. Because if both were bigger than L over 2, that inequality could not hold. So at least one must be smaller than L over 2. And on the A's, there must be an AI that is less than or equal than L over 2. It might cut it in different ways, or it might cut it equally, but that has to happen as well. So then form the curve gamma tilde, which is Li plus AI. So you say the left side of this picture has the shorter end, and the AI that goes here has the shorter end. And then this geodesic, this curve would have length less than L. Gamma tilde would have length less than L, because Li is less than L over 2 and AI is this. So this curve that I've drawn here would be short. So the only possibility this is not a problem is if this curve is not trivial, it's not non-trivial, if this curve is contractible. But if it was contractible, this whole piece, L1, this whole piece, L1, could be folded into A1, and this whole geodesic would have been on the right side of the surface, the red geodesic. So that we know there's no geodesic that is bad in the right side of the surface. So that contradicts the hypothesis. So this leads to a contradiction, and therefore we cannot have a geodesic smaller that crosses this smaller than L. So it doesn't happen. So actually the length condition that the Color Theorem required, that L be less than L star, L less than L star, is only needed for loops. The classical closed string field theory, hyperbolic closed string field theory, exists for L arbitrary. You can still get everything to work, and there's no problem with the systoles and the sewing, because this argument shows that there's no way you can get a short curve anyway. That argument would not work in a loop case. The argument is it just fails. So anyway, we got our answer, we got our claim. So we are in reasonably good shape. The systolic vertices are therefore determined, and they are just those surfaces in this section for which the systole is bigger than L, with L less than L star, and those will cover the moduli space. So I want to end with two remarks. We discussed this beautiful section of MGN, which is produced by this hyperbolic section, which comes from GR infinity prime of MGNL. Purely hyperbolic things and just tubes for the punctures, and that has a region that in which the systole is bigger than L, but the rest is there, and this is a section. On the other hand, you know that the Feynman graphs cannot produce this, because Feynman graphs of string field theory require sewing of other vertices, so it can give a different thing whatsoever. So what do they give? Well, what we explained last time is that when we saw together two of these vertices, we put a flat cylinder in between, just like we put flat cylinders at the punctures, and that gives you a consistent picture, but it represents a different thing here. And we call it the FGN for Feynman. So Feynman agrees with the vertex, because the vertex is the only part where is the simplest Feynman graph, but then the other ones is here. Now you can ask, this is by inserting flat tubes when you do the sewing. Why is this natural and does it work? We argued that there was no way to glue hyperbolic annuli. So getting a purely hyperbolic picture of this thing is not in the offing. No opportunity to that. We cannot glue hyperbolic annuli because they create curvature singularities. So if you have to glue these things and define a metric, the flat seems the nicest option. These surfaces that are mixed, there are in some regions a hyperbolic vertex flat, and they go on like that. There are mixed surfaces that were considered by Thurston, the mathematician, in the study of projective structures of Riemann surfaces, which is a big field. I don't have time to even discuss it. But these metrics exactly of this type, mixed hyperbolic and flat, appear in this theory, which suggests there's something interesting. In fact, in conversations with Matt Hedrick, he came up with an idea that we've been working on, and we're trying of inventing a minimal area problem that would define these Fs. Minimal area problems are very nice in general, and in this case, it would make the problem quite natural. So here is the candidate problem, minimal area problem, that would establish this and would help establish that the F is actually a section. At this moment, there's no proof that the F is a section. For all we know, this F could turn and do funny things and do things like that. We don't think it does, but it could be. So,
Barton, even for small enough L, you cannot prove that F is a section?
I think you can prove it for small enough L, but I don't think we have a rigorous proof. It's it's hard to do those rigorous proofs. We have almost a proof that it's a section everywhere, but almost a proof is not good enough. So let me suggest, let me give you a problem. Here is a natural problem. Let me, Harold, I probably need 4 minutes to finish a Renan.
You have finished your time, but you can go on. Just take time from your Q&A.
Okay. Suppose I give you a Riemann surface here, and I ask you, find the metric of least area such that the curvature is greater than or equal to -1. Here is a minimal area problem to solve. This is a compact Riemann surface, some genus G, sigma of genus G, no punctures. Well, I claim the answer is the K equal -1. So if you put this constraint K greater than -1, the answer is the K equal -1 metric. And this actually comes, it's simple to prove actually, is you consider the Gauss-Bonnet theorem that says, equates the Euler number to the integral of the curvature. Then you say curvature is equal to -1 plus some delta K, but this problem says that delta K must be greater than 0. So you get 2 minus 2g, 1 over 2 pi, integral of K when it is -1, the A gives you minus the area. And then you get plus 1 over 2 pi integral delta K dA. So the area, you solve this, you get 2 pi 2g minus 2 plus delta k dA. And then you see that if delta k is positive, the minimum value of the area happens when delta k is 0. And therefore, you do show that delta k equals 0, k equal minus 1 is the minimal area metric. So inspired by that, we claim that this Thurston metric, this mixed metrics of the hyperbolic string field theory are solutions of the following problem. Given a Riemann surface, minimize the area subject to 1 systole greater than L and 2 k greater than minus 1. So this is the conjecture that the minimization of this this minimal area problem. So I sort of like the idea that all the cuts of all the decompositions of moduli space come from minimal area metrics. It's elegant, and this probably works because you basically have on the surfaces they consider a surface is either a region where 1 is saturated, k is equal to minus 1, or there are geodesics of length L, that there are cylinders. And there cannot be overlap between these two regions. And on a hyperbolic surface, like I argued, k greater than minus 1 forces k equal to minus 1. And we know that if you have a region with geodesics that saturate, it really must be flat. So it's fairly intuitive, but there's no proof yet that this is the answer to the problem, and makes it natural from another viewpoint. The last thing I want to say is that for the case of the 3-string vertex, if you want to begin doing calculations, off-shell calculations, as Yuji mentioned, you need the local coordinate expressions for this problem. And this problem is difficult. And when I asked mathematicians, they didn't quite seem to know what the solution is. And this was solved by Firat. And there's a paper of last year or this year, beginning of this year, or it's 21/02/0393, in which in fact, there are techniques, and some physicists have developed all kinds of techniques to do this. So in some sense, was a matter of isolating the techniques that were necessary to turn the Liouville equation that is impossibly hard to solve into a Fuchsian equation that is much easier to solve. And without that, I think the problem would have been extremely difficult, and I recommend that you read this paper. So the off-shell 3-string vertex is known, and it can be calculated. It was calculated for arbitrary lengths. So in principle, that says with the Fenchel-Nielsen construction, you can build anything. Now, principle and practice are not exactly the same thing, and maybe the results of Firat need to be simplified further or understood yet in another way before the sewing can be done efficiently. Maybe somebody will figure out how to do that, but at least this is off the ground, and you can calculate a few things explicitly if you wish to. So with that, I'll finish. I'm done. Thank you very much for your attention. It was a pleasure to be here, and thanks again to the organizer, chairman of the session, Renan, and all of you for your questions.
Okay, thank you very much, Barton. It was great to have you here, and always a pedagogical as usual. We're very happy to have you as a lecturer.
Thank you.
I have some comments now before I open for questions again. Today we're finished with the lectures. Tomorrow we'll start with the research talks. We still have a Q&A section today for both Barton and Olaf. I would just like you to like to remind you that tomorrow, before the official beginning of the research talks, there will be this conference branch. So I guess all of you have already received the link for the Gathertown. It's something that we're trying. We think it can be fun. It's a like a very easy way to gather in these online times. So we hope to see you there, so you can join and introduce yourselves and so on. I don't know, Harold, is there anything else I should comment on this? Okay, Harold is posting the link for the Gathertown in case you haven't received it. But I think
I would say maybe we can take a 5-minute break before starting the Q&A, just to, break.
Yeah, I was just going. Yeah. So we can have a 5 break. So we can restart 6:25 local time here in Prague. Yeah.
Very good.
See you soon. So we'll start with the Q&A section. Olaf is around, I can see. So yes. I think in the schedule, Olaf goes first. So we can start.
So I have a question for Olaf. When you do the computation explicitly, so with the different field theories, is there any way to see directly what is the degree of some expressions? So, like in string field theory, we always have the ghost or in the word line to know what is the degree, but here, is there any things if I give you an expression, or just you have to remember from where it comes from?
Yeah, you kind of have to. I mean, if you don't tell me what that is, just a random expression, and you don't tell me in which context it shows up, I think you don't know. So it's sort of a bookkeeping device where you have to remember in which context it plays a role.
Okay, and kind of a related question. So in the word line, you can get the L infinity using the ghost. Is there any relation between this L infinity and the one you wrote? Like if you do the word line for young meals and you want to write the infinity in the word line and the one you get, is it, is there a direct relation, or you have to do some things to get from the one from the other?
You see, from the word line formalism, you get an L infinity algebra.
Yes, if you follow what we do for string field theory, but with the word line, so you introduce the BRST symmetry on the worksheet or word line, and from there you can move to L infinity. So I was wondering in that case if, how it relates to the one you introduced.
Yeah, I'm not. I know about the word line formalism, the word line approach, but I'm not familiar with that particular construction of an L infinity algebra, so I don't know.
Okay, so I'm just know the one.
Can I ask?
The case of
following this, can you hear me?
Yes, we can hear you, Ted.
Oh, okay. This is Ted. Is there really a word line formalism for pure Yang Mills? Does anybody know?
I think so.
Is the spinning particle n equals 2 is like the word line Yang Mills when you put it in a background that is non-abelian.
And it doesn't have any space-time supersymmetry or anything other fields, or?
No, in this case, if you just think about the spinning particle, it is just like local, like word line supersymmetry, so to call it, and it gives you just Yang Mills.
Okay. Okay. So, so kind of following up on Harold's question. So if you do like world line, like world line BRST for the scalar particle, or just then you naturally find ghosts. And these ghosts, I guess, could, so basically your Klein-Gordon operator gets multiplied by a C. And then these ghosts could be used as some kind of a bookkeeping device, which would allow you to keep track of these gradings, at least in the case of scalar field theory.
But the point in the scalar field is that it's kind of trivial because you have only one ghost. You know, it's not like in string field theory where the ghost is depending on Z, but here you just get C, and kind of all the L infinity relation are 0 just because you get C square everywhere. So it's kind of sort of trivial for just the scalar field. So it's why I was wondering, so Olaf was saying that it's also kind of trivial in his case because you don't have I mean, you just have x0. So I was wondering if it was the two triviality were related.
I mean, you can introduce, I think you can introduce such a ghost, auxiliary ghost as a bookkeeping device. But I mean, it's, as you said, it's a trivial thing, I guess. I'm not sure if it actually helps you.
So I have another question, maybe it's related. So, okay, in the case of Hamiltonian quantization, we kind of have a very systematic procedure of starting from the Lagrangian, deriving constraints and figuring out what the ghosts and the B ghosts should be, and constructing a BRST invariant formulation of the Hamiltonian theory. So there's kind of a recipe that you can follow starting from the Lagrangian. Is there a recipe? Have you articulated a similar recipe at where I can just give you a field theory Lagrangian and you will be able to figure out systematically how to write it in L infinity form? Or do you kind of have to like look at the gauge parameter and say, okay, that's going to be it's going to be del 1, and look at the at the equation and call that del 0, or is there some kind of a?
I mean, I would say what I
articulated,
what I sketched in the lecture is sort of a recipe. I mean, you look at given a Lagrangian, you know the equations of motion, and you can read off the brackets to arbitrary order for the fields. Now, so that's completely algorithmic, I would say. The issue is that it's just given a Lagrangian, you may not know what the gauge symmetries are, or if they're gauge for gauge symmetry. So that requires an analysis.
Yes.
But usually we do. I mean, suppose there's a gauge symmetry that I overlook, then I would not include it in the space of gauge parameters and perhaps get in trouble at some point.
But then there's a point of self-consistency, right? Like if there's some gauge symmetry that you didn't include, it should show up. Unless it's something that's completely decoupled, then it doesn't really matter, right?
Right. At some point, you would expect that you get into trouble if you overlook a certain gauge symmetry. But I mean, if you correctly identify the gauge symmetries and gauge for gauge symmetries, etc., and hence the corresponding Bianchi and Bianchi for Bianchi identities, etc., then there's I would say there's a clear dictionary to read off the corresponding L infinity algebra.
But then isn't this question of the grading just like trivially solved in the BV formalism? They have a clear structure, ghost number, anti-field number, and so on.
Yes, yes. If
It should be.
if you're happy with that, then there's no problem.
Hi, I have a question. So when we discuss the dictionary between L infinity algebra and field theory, how does that change for a supersymmetric theory?
Yeah, that's a good question. I don't think, I think not at all. It's just you get further substructures or further gradings. So your space of fields can contain fermions. There's no problem with that. So you can also have it in a supersymmetric combination. And just means that the differential will contain a component that is, let's say, the Dirac operator or something similar. I don't think anything really changes. So then, of course, there's a further grading because you can decompose the space of fields at degree 0 into an odd and even part. So, but that's not a contradiction. You can have more than one grading.
All right, thank you.
So in particular, that some objects sort of in the scheme get a fermionic character. It doesn't mean that they are really fermions or really bosons. It's just an accounting trick, if you like. So, for instance, if you we have in this convention I'm using, which is already just a convention, so nothing fundamental. The fields at degree 0, and hence you think so even objects in this grading. So naively you think they must be bosons, but that's not true. And you can see that if you go one space over the space of equations of motion, in this counting, it's a degree -1, so it's of odd degree. But if you have a boson, and if you scalar phi and you look at box phi, you would not think of box phi as a fermion. And of course, it's not a fermion. It's just that within the scheme, you have this grading that you need in order to keep track of the signs in the L infinity relations, and that's it. It's nothing to do with bosons or fermions, as in the sense of fundamental space-time fields being bosons or fermions.
So this grading does not have anything to do with the supersymmetric grading of fields?
No.
Okay, yeah, thank you.
I have a question as well. Just so you can ask it. So
yes.
So there was this discussion about the existence of solutions, and you
yes.
gave this nice perturbative proof that solutions exist.
Yes.
And I wanted to ask about so Barton was mentioning that the argument was necessary but not sufficient, and there was some additional conditions.
So it's good that you remind me, because I wanted to come back to it, because I wasn't happy with the discussion at that point. So so let me just make a few clarifying remarks. So the natural notion of homology in this context, which I used in this discussion of homotopy transfer, has a straightforward physical interpretation. So if you look, for instance, at the lowest order equation, I don't think I have to put my notes up again, but it's like perturbatively, the first equation is just partial A0 equals 0. That's what you want to solve. And of course, we're only interested in solutions up to gauge transformation. So any two solutions that are related by gauge transformation, we view as equivalent. And that's just the statement that the space of solution is the homology of H0 in this convention. So the homology H0 is the space of solutions to del 0 A equals 0 up to So you identify any two A's that are related by something exact. So that's the notion of homology. So what that encodes, that homology is the space of non-trivial solutions of the equation. So in other words, if the homology is trivial, there are no solutions. All solutions are pure gauge, in other words. So that's one thing, which is the notion of homology that shows up here and is natural in view of this homotopy transfer story, because you would say the real physics is in the homology. The actual formulation, so the specific L-infinity algebra you use, may have all kinds of extra stuff, gauge degrees of freedom, etc., etc. But the real physics is in the homology. So if the homologies are the same, you may go from one to the other. So that's an intuitive picture. But then I'm not so sure about this. The others, it doesn't look like to be the same kind of homology-related discussion on solving equations that Barton was using, because there, maybe Barton can join in. So maybe we can use this opportunity to have a discussion now how these two things are related. Because you seem to need a trivial homology in order to get a solution, which is sort of the opposite of what I was just saying.
No, but when you go and try to solve for A1 or A2 or A3, isn't it sufficient that those are trivial?
Sufficient? What do you mean? That A1 and A2 are trivial, or?
Well, at the end of the day, the equation for A1 is dA1 equal to something. Is that right?
Right.
Is that something trivial or is not trivial?
Well,
it's close, but is it trivial or not?
I see.
I think.
Yeah. So what the analysis shows is that it's closed, but
so you need the right-hand side to be trivial, is that right? Because it's equal to dA1, so that is a trivial thing.
Oh, I see. So that's what you meant. Yes. Okay. So the equation. So the next equation is something dA1 is it was bracket A0, but the details don't matter. But the L-infinity relations allow you to establish integrability, which is if you hit it with another D, the first term of course drops out, and the second one is also 0, so it's closed. What Barton is saying, what you really need to solve this equation is to construct an A1. So you have to solve the equation partial A1 is equal to that thing. So that means that thing must be trivial because it's equal to del 1, del of A1. Hence, the homology in that piece should be trivial, right? That's what you're saying. Okay.
Wasn't there some argument that goes beyond the perturbative analysis? Or
well, I mean, this perturbative analysis was a particular integrability condition that you need to obey in order to have any chance of having perturbative solvability. That doesn't exclude that there are other obstacles, or I mean, doesn't establish that there's always a solution, I think. It's just if that doesn't work,
but
then you can't do perturbation theory. And so that was the point I was trying to make.
But can one state a clear condition that would be sufficient for the exact solutions to exist? And what would the condition be? Which doesn't rely on
perturbative analysis. I mean, you may run into obstructions if there are, for example, massless tadpoles. I mean, if you are trying to solve these equations perturbatively, and if there is a massless tadpole, then you run into an obstruction.
Okay.
Because that's precisely the statement that you cannot solve the equations of motion.
Okay, so is that the only kind of obstruction that can exist? Or
perturbatively, I think yes. I mean, that's the only kind of obstruction that, by definition, in some sense, right? Because you are solving, you have a right-hand side, right? And you cannot solve it. That means that 1-point function is non-zero.
Yeah, so I think this should be related to the possibility of having flat directions in the potentials described by this solution you are turning on, right? So you are giving some finite web to some fields that is to the first order described by this phi 0, then you add phi 1, phi 2, phi 3, and then this if this thing exists, it's going to be a one parameter family of solutions, right? So that means that your potential should have a flat direction. Now, this is not guaranteed. This depends on the potential. So in general, that equation will not be solvable. So in string field theory or string theory, this is the issues of exactly marginal deformations. I mean, not all massless fields will generate flat potentials, right? Just think about Ian Mills, for example. So I think in general that equation will not be solvable. I mean, it's integrable in the sense that the L infinity relations assures that the equation is somehow consistent, but that doesn't guarantee that there is a solution for chosen phi naught, right? So if you just take an element in the cohomology of del, this phi naught that's just solved del phi naught equal to 0, that doesn't mean that this will be extendable to a full solution.
So how does one proceed?
Yeah,
I mean, how?
Yeah, so you can
what's
imagine,
the best one can do?
Let's suppose that you have a scalar field, massless scalar field, with a phi to the 6 potential.
Yeah.
Okay. So you try to solve perturbatively, right? First order, there's no problem. Phi equal to constant is the solution. Next order, there's no problem, right? Till you hit the contribution phi 5 order, right? Because phi to the 6 will generate a term in the equation of motion, which is phi to the 5. And there you see that arbitrary constant phi is not a solution.
Right.
Right, and these things does happen in string theory. I mean, that you find the stat poles at high order often.
But is the conclusion that the equations Olaf was discussing to solve the equations recursively is that there's no contradiction, but there can still be obstructions at each order, is that right?
Exactly, yeah. So I think the equations are still perfectly consistent with each other. It's just that there are no solutions.
Right.
That you cannot generate the solutions iteratively. So.
Right. So the consistency condition is that those right-hand sides are closed, but they actually have to be trivial, and it just may not happen.
Yeah. So I don't think there is any problem with the L infinity algebra as such.
Right.
So these integrability conditions are really only relevant in gauge theories, of course, because otherwise the differential squaring to 0 doesn't give a condition. But the Ashok's example showed that just taking a scalar field, you can just give an example where you can't solve the equations perturbatively, but yet the equations are trivially integrable in the sense I discussed. So it's just a particular consistency condition that you want for gauge theories, I would say.
Yeah. So the consistency condition seems to be that the right-hand side should be closed, but it need not be trivial. That if it is trivial, then there is actually a perturbative solution. If it's not trivial, it's still okay, right? I mean, L infinity algebra is still okay.
Right. Yeah, the L infinity algebra doesn't say anything about that. I think there's no problem.
Yeah, the L infinity algebra would say, in principle, there may exist solutions. You cannot. There's no in principle obstruction. Could be in practice obstruction.
Yeah, exactly.
But in principle, all these tadpoles can be cancelled, right? By appropriate field, by appropriate shifts, field redefinitions, or
no, I don't think so. I mean,
by appropriate shifts.
Imagine that you have a massless scalar with phi to the 6 potential, right? the only solution is phi equal to 0. You cannot get a solution at non-zero phi. Right? Constant solution. Even though for first few orders, any constant phi is a solution.
Okay, so I think we have passed the 20 minutes for Olaf. So is there any urgent question, or otherwise we can move to the question to Barton? Okay, seems that there is no more question for Olaf. Thanks again, Olaf, for all the answer and for the lectures.
Thanks again for asking me.
Thanks. So any question for Barton?
I have a question.
Yeah, Nichai, how are you?
Hi, Barton. How are you doing? Yeah, thank you for the great lectures. So in the last part of your lectures, you posted this minimal area problem.
Right.
Where is L star there? L star, the critical length.
Yeah. Right. So yeah, I think let me just go back to the notes in case this is helpful. I go here and share content, share screen, start broadcast. Okay. So I mentioned this possibility. So in principle, okay. So I think your question is whether this problem goes weird or strange,
right?
If L is different, smaller than L star. Is that right?
I mean, greater than you meant.
Yeah. So what would happen? So yeah, that's a good question. So if you were sort of just looking for something simple, you would say less systole greater than L, but still smaller than L star. That would work. Now, if you would do just systole greater than any L, you could get by for genus 0 and any number of punctures, because the closed string field theory will work for that question. So if
shouldn't there be a modular transformation that maps you back to the good region?
Not sure. Let me continue. But yeah, there's so it's I guess I'm not sure what goes wrong in general if you go with systole greater than L star. It might you could imagine something going wrong at higher genus, or the surfaces not looking the way I expect them to look, like disjoint regions where either the curvature is -1 or 0. So actually, yeah, you know, I think there may be a problem here. Okay, so maybe the way to analyze it is, suppose you take a surface of genus 2, and you put the condition k greater than -1, and if you just had that condition, I just showed or explained in the lecture that the answer is the hyperbolic metric.
Right.
But then if you look at the hyperbolic metric, say for the Bolsa surface, the systole is like bigger than L star. So the systole is like 3 or 4 or something like that in the Bolsa surface. So if you could put, for example, a condition k greater than -1 and systole greater than 5, then you're not going to get the standard hyperbolic metric anymore. So they will interfere with each other. So I think what might happen is that the solution might be exotic in that case, that you may actually flow to curvature maybe -1/2 or -1/3 until you get there, or something like that. So you may not saturate it. So I think basically the problem becomes more complex when you put a systole condition that is large in general. You see, the simple case is that when the surface has no boundaries and nothing, and then condition number 2 is very simple and likes it. But then if condition number 1 then doesn't work, then you don't saturate k-1, so it's going to be more complicated.
I see.
So I think the expected solution will not be this dichotomy of flat curve, and all curves with -1. It will be just something funny will happen.
I see. Oh, thank you very much.
Sure. Good question. Yeah, I hope we'll try to finish this work and really do it, because conjectures are not good enough.
I have a question.
Yes, Ted. Hello.
Hello. I think it was my understanding was a big motivation of Pius and Musavian, that somehow this picture could help you integrate over the moduli space.
Right.
And I was wondering whether this motivation is still operative to you, or whether you have some opinion about it.
Yeah, I think the motivation is still there. I think there's a real chance that I certainly I've been pushing for many years the minimal area metrics, the polyhedra, and all these things. And I tend to believe that for classical solutions, probably the polyhedra are easier to use. But in terms of calculating the action more explicitly, the terms in the action, I think this approach is good. So I think, in fact, a lot of the work that Pius and Musavian didn't get to the point where they used their vertices that were cuspy. Those cuspy vertices need corrections, and they're harder to use, I think, in general. But maybe all the results hold as well. And in fact, since the Fenchel-Nielsen construction is really perfect for the string vertices, the string vertices are purely hyperbolic, and therefore the Fenchel-Nielsen construction works for them. The difficulty again is that, well, let me say it this way. There's the big Teichmuller space, And well, that probably, I shouldn't draw it like that. The big type Mueller space. And here is the moduli space. MGN, TGN, L, or whatever. And the moduli space appears in infinitely many copies in the type Mueller space. Now, the action is determined by nu GNs, nu GN in here. And then the question is, well, we want to do, the mathematicians figured out sort of how to do integrals over MGN by starting with integrals over the whole type Mueller space. What we need to do is integrals over nu GN, and that's the challenge. Now, do you need to look at the copies of nu GN in the type Mueller space? I don't know. I think this is a good thing to investigate. Now, all the nu GNs can be constructed by sewing together pants of different lengths. So if it's an external leg in the nu GN, it's LL, but the internal ones are here. So at least from the viewpoint of maybe trying to do a little more concrete problem, one could try to figure out, for example, how in the Fenchel-Nielsen construction you have L, 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 and two parameters, L prime and theta prime, which is the length of the intermediate geodesic in the pants and the angle. So how does nu04 get described in terms of L and theta? I don't know. Is that necessary to do integrals over nu04? Do you need to know what is the ranges of L and theta, L prime and theta prime?
But at least the Fenchel-Nielsen coordinates are somehow, they're naturally given to you on the vertex region of the moduli space.
That's right. The Fenchel-Nielsen are naturally there in the vertex region. So that's a great simplification. And I think Pierce and Musabian also figured out that the anti-dosed insertions for this moduli were very geometric, for the Fenchel-Nielsen moduli are very nice and very beautiful. Whether the integrals can be done, that still remains to be seen, but maybe some of the tricks that apply to go from T to M will apply to nu. Ashok was mentioning yesterday that in the limit as the systole length L is much less than L star, in some sense the vertices almost cover the hyperbolic section, and maybe you could begin by trying to do this computation a la Fenchel-Nielsen with boundaries very tiny, and then try to do corrections to that. But an exact determination of the vertices seems in principle doable. So
okay, but even like expressing the Veneziano amplitude or the Virasoro-Shapiro amplitude as an integration over Fenchel-Nielsen coordinates, I don't know if anything like that has ever been done before.
No, it's not been done because
on shell.
Yeah. Well, just to say, not really, because all the formalism, all the old formalism of region and so on was built in such a way that you could go off shell. It's clear that it is an arbitrary way of going of shell, but they are in a certain sense of shell. And actually, they need to be a little of shell, otherwise you cannot glue together and go through the sewing procedure. So they are in a certain sense of shell. But the point, which is not clear, is how you go further, in the sense that you know the free vertex for the closed strings, and then you can sew together and you get a four amplitude. But you are probably missing the V04 in this formalism, probably because you are overcounting the modular space, or I don't know, but in principle you are of shell. This is the point. So you should be able to implement, at least theoretically, the L infinity algebra.
I see. Yeah, I think these computations are going to require a little cleverness and some ideas, because they're promising, but they're still very difficult. So just calculating the Veneziano amplitude of shell in the Witten theory, in principle you can write it, but since the conformal maps are complicated with elliptic functions and all that, the answer is fairly complicated. Now we did manage, I think it was doing this with Rastelli, to calculate the off-shell Veneziano amplitude and Schnabel gauge. So there's issues, the Siegel gauge is the one that has the closest image in the sewing of strips or cylinders. So, but on the other hand, there are more exotic gauges in open string field theory, and there may be more exotic gauges in closed string field theory. So you might start with a hyperbolic vertices, but still do some kind of exotic gauge fixing, and then maybe the problem simplifies. I think it's not quite clear exactly how to do things.
So this raises another question that I was confused about. So you were saying that it's not a good idea to sew these hyperbolic vertices together with hyperbolic annuli.
Right.
And okay, first of all, I didn't fully appreciate that comment. And second of all, I'm not sure what is a hyperbolic annulus from the point of view of gauge fixing a string field. I don't know if you can comment on these things.
Well, this the metrics at the end, there's a thing that in fact the calculations don't require metrics. They calculate they require local coordinates. So in order to do metrics, you do metrics in order to find local coordinates, but in principle, the calculations don't require local coordinates. So, in fact, it may be that some aspects of the integrals that you need to do are better understood in terms of metrics, integrating over metrics as opposed to integrating over the local coordinates. So you integrate over hyperbolic metrics, and then it's the same thing as integrating over modular space. So in this sense, you see, once you have I think one should emphasize this. If you have two boundaries, then there are local coordinates here induced by some quantity, a z and a w, and in principle, all you are supposed to do in order to represent the propagator is to do ZW equal T and integrate over T inside the unit disk. So there's no need to say, oh, well, I'm inducing an annulus and we're doing things like that. You're basically, conformally speaking, you are introducing a little stop here, you're introducing a little stop, and you're gluing it. But the picture is that you have a Riemann surface, and you had a hole, you had another hole, and you now put a disk, and then you simply cut a hole, and glue those. So there's no need to speak of metrics, but given that part of the section is nicely defined by metrics, you try to define the rest of the section by metrics and try to find a section over moduli space. So these metrics help you gain control over things, but they're not absolutely necessary. So indeed, the Feynman region can be described just in terms of complex coordinates and gluing. But if you want to have the ability to show whether there's a section over moduli space or not, you're better off with the metric. Right. So nothing in principle says you cannot use those things, but in practice, it becomes complicated. So if you have a local coordinates and well, if somebody gives you a surface and it has some sort of discontinuity in the curvature at some place, it's going to be pretty hard to calculate the local coordinates for this global metric. It will become a very complicated problem. So it's just that.
What about, isn't there, in one of Polchinski's old papers, 1989, which I think, if I understand correctly, I think you looked into at some point, where he explains how to cut open these handles and define a metric in a globally well-defined way for arbitrary curvatures.
Well,
that might be useful in this context.
I do remember Polchinski's analysis of dilatons, in which he, in fact, he used metrics as an auxiliary way to integrate dilaton insertions over surfaces. And that was a very natural thing because the dilaton is not a primary field, so it couples to the local coordinates. So you could use local coordinates with a very abstract description, but if you take into account the way the dilaton gets transformed by the local coordinates, if the local coordinates come from a metric, then it's a simple coupling of the dilaton to the metric. So,
and there's also a natural generalization to the superstring.
I imagine.
At least for the NS sector.
So metrics are auxiliary at the end of the day. So one shouldn't be too afraid to do exotic things with them. But
in fact, in my paper, in a recent paper of mine with Dieter Lust, we review that construction in quite a lot of detail.
Oh,
I don't know. Perhaps it's of interest. It's a paper called Handle Operators in String Theory. It's quite a long paper.
Should put it on the chat so you can see it.
Let me find it.
Yeah, I have a general question. I don't know whether it makes sense and whether somehow using vertical segments so that you can simplify the string vortices. I mean, it looks like you are making it more complicated, but I think what I mean is, a lot of the constraints on Newgians come because they have to match the Feynman diagrams, right?
Yes.
Now, if you allow vertical jumps across the boundary,
right,
then that constraint goes away, but you have to add those extra contributions.
right.
And
right.
I wonder if that could help simplify some of the explicit calculations. Of course, at the end, I mean, there is no difference. It's all gauge invariant. It will have the L-infinity algebra and so on.
Right. So you're saying if you have MGN, then you may have a new GN. Oops, I will erase that. So the new GN itself is discontinuous or not? Or the
Well, new GN could be continuous or discontinuous, but I'm thinking more that at the boundary, it could be a discontinuous jump.
I see. I see. So,
so the equation that you the boundary of new GN is equal to something.
Yeah.
That should hold for MGN, but not necessarily new GN because you can allow vertical jumps.
I see. So you're saying that the region with one propagator that is supposed to match here instead matches. It's just on the vertical line, PG.
That's right. Yeah. Yeah.
I see. So, so basically, that means that at least in simple ways, it means that the vertex reaches the surface with the same moduli, but the local coordinates are different at this point.
That's right. Yeah. Yeah.
So, don't you? I presume that that erases the constraint, but makes it necessary to define the vertex by having an extra contribution. Is that right?
Yeah.
A red contribution.
Right. Yeah. Yeah.
And I thought, in some sense, that was the supermoduli space explanation of the contact vertices. Yuji, I think, used to do that. Of the contact vertices in the Berkovitz superstring field theory, that somehow all these contact vertices were places where things were matching, but the supermoduli were not matching, and they were adding the contributions for supermoduli to match, or something.
That's right. Yeah. And so in the superstring, it seems to be necessary. For bosonic string, it doesn't seem to be necessary, but nevertheless, it may be useful.
I see.
For some practical details. I don't know. I think it's just a thought.
See. So you would formally include in the vertex the vertical segments, or no?
That's right. Yeah. Yeah. So maybe I'll rewrite the equations in a little differently. That besides the what you have, you also have this extra piece.
Okay.
Right, the vertical piece.
I see. I see. And the vertical. So the whole section, the whole Feynman region is some new GN plus some vertical piece plus things with one propagator, and then things with two propagators, and maybe vertical pieces at every stage.
That's right. Yeah. Yeah. Exactly.
Actually, regarding the necessity of this, isn't it also possible? I think, wouldn't this? Hello, can you hear me?
You disconnected yourself.
Sorry, isn't the superstring generalization of Polchinski's construction? Wouldn't that be correspond to a smooth section, which wouldn't require vertical integration? I mean, in principle, isn't it possible to construct a smooth gauge slice, which doesn't which
I think there is no proof that it's possible. And
but
this Donaghy-Witten analysis already shows that it's not possible holomorphically.
Holomorphically, yes, but the Polchinski gauge slice is not holomorphic; it's a smooth. And,
yeah,
and
but I don't
as
think
far as I understand,
there's
no obstruction.
It exists on all Riemann surfaces.
Sorry, can you repeat that?
So it's a covariant. It's covariant. So one can define things in terms of covariant objects like supercurvature and covariant derivatives, so that which extend naturally to the entire
But there may be global obstruction, right?
I don't know. I don't know if there would be. So what
There
kind
can
of
be.
global
But
obstruction?
I'm saying that you have to prove that there is no global obstruction.
Because I thought, I mean, isn't the vertical integration a particular example of a smooth gauge slice? Which is just of a special, very special type.
No, vertical integration is not a smooth gauge slice, right? It has discontinuous jumps.
Yes, but isn't it sort of a limit of a smooth gauge slice?
No,
and
no,
more generally,
because the point is you cross singularities on the way, and then you have to make special efforts to show that the singularities don't matter. And if you try to smoothen out this, then the singularities will matter. So vertical integration is a very specific procedure by which you avoid the singularities. That even though you're crossing singularities, you show that the result is independent of how you cross the singularities.
So the gauge slice I'm referring to is independent, before we integrate out the gravitinos. I'm not referring to the PCO construction with the delta function gravitinos.
Yeah. These are the delta function with the picture changing operators.
Yes, the smooth gauge slice I'm referring to is before one reaches, without integrating out.
But I don't think there is any proof of existence of smooth gauge slices over the whole Riemann surface, or the whole model.
Yes, but I don't know. I was briefly had some correspondence with Edward about this, and he seemed to think that there may not be any obstructions in that case. But I don't want to misquote him.
Yeah, I don't think anybody has proven that there is an obstruction. But on the other hand, nobody has also proven that there is no obstruction.
Yes. Okay.
I mean, the Donaghy-Witten analysis shows that there is a obstruction to holomorphic sections.
Yes, but this is independent of that.
Yes. Yeah, but if you don't demand holomorphy, I don't think there is a general proof that there is an obstruction, but also there is no general proof that there is no obstruction. That's my understanding of the.
I see.
Of the situation.
I think it's an interesting question, though.
But
I don't know.
Yeah. I think Tate has thought about it. I don't know whether he has some.
Who thought about this?
Tate Erler, I think, has thought about it a lot.
Ted Erler.
Yeah, I think he
Sorry,
had asked about questions on
I
this.
disappeared for a moment. What was the question?
Yeah, whether you really need vertical integration in superstring theory.
I don't know. That's too sophisticated question for me. But I asked people and nobody seemed to know. So, but maybe you don't need it. But
is this
okay? You can have it.
Is this a question that has a formulation purely in the context of bosonic moduli?
Well, I guess you could. I don't understand supermoduli space and super Riemann surface formulation of all this very well, but I think you could ask, for example, whether there is a. Okay, so Ashoka introduces this fiber bundle where, in addition to the moduli space and fibered, you include coordinates over where you can insert PCOs on your surface, right?
Right.
So you can ask whether this this bundle has a smooth global section. So, and I don't know whether it does or not, and I don't know. I also don't know whether the claim that supermoduli space is not holomorphically projected, how that relates to a condition at the level of PCOs on your Riemann surface, and whether that means that they can't vary holomorphically with the moduli, or okay, but one difference between the superstring and the bosonic string when it comes to vertical integration is that in the superstring, if you integrate along a vertical segment, okay, in a specific way, the measure becomes a total derivative. And that's really essential for jumping across these spurious poles. And it also makes for simpler expressions for these vertical segments. But I don't expect the same would be true if you're integrating vertically the local coordinates. I don't see how that could be formulated as a total derivative with the measure. So I would say that it doesn't help that much to have these vertical segments, to put these vertical segments in your decomposition of moduli space.
Let's see. So there's the points where you insert vertex operators. There's one kind of punctures, and then there's the points where you insert PCOs, which are other kind of punctures. And
right.
And somehow you need the vertical segments corresponds to motion of the PCOs while keeping all other things fixed, presumably. Is that right?
Right.
Or during the vertical segments, do the local coordinates of the vertex operators change as well, or
not? I think in principle, no. Okay, I think in the formulation of Ashok and Witten, they don't even have local coordinates. So you could consider this somehow an on-shell version of this problem where you just have the moduli space and your fiber is just the location of the PCOs and there are no local coordinates.
But I think in the field theory, you will keep the local coordinates fixed. As you
could for the PCOs, you don't need a local coordinate, is that right?
No. Because those are dimension 0 coordinates. Right. Dimension 0 coordinates, yeah.
I see. So it's just a set of positions. Yeah. And but you don't want them to collide as well.
Well, see, it's not just the collision, because that would probably have been simpler, because there are also a lot of spurious poles which are not at the position where they collide.
I see.
It's a complicated equation involving the Riemann surface moduli and the PCO locations and the locations of the other vertex operators. So, and you have to make sure that you avoid those as well.
I see. But there's no purely geometric condition that says, oh, you have these vertex operators and you have those PCOs, but that surface is bad because it gives you singularity. Is there a way to...
Yeah, there is a geometric, well, I don't know whether you call it geometric. There is an equation involving theta functions.
Yeah.
Which one vanishes, give the bad surfaces.
So those should be called bad surfaces to be avoided.
Yeah.
So you need to sort of find the topology of those sets of bad surfaces.
Exactly. Yeah.
Wow.
I think that's what makes the problem hard, because those equations look very complicated.
I see.
But isn't that closely tied to the choice of gauge slice?
Yeah, it
because
is.
If one, yeah.
But what is not clear is whether we relax in the gauge slice, whether you can avoid this problem altogether.
Yes. I see.
Right. See, on a local,
I can imagine it being much simpler because the theta functions, they mix all of the moduli in a very complicated way, whereas the analog of Polchinski's gauge slice decouples all of the moduli as much as possible, in a sense. So I would imagine it being much simpler because everything becomes kind of local.
Yeah, but my understanding is that choice is local in the moduli space, right?
Yes.
You have to make sure that it
in
extends
super moduli.
That's where the problem is. See, at a given point in the moduli,
it's covariant.
Is a good gauge size.
We're
a
going
covariant
a bit
construction,
over
so
time.
shouldn't
I
it?
think this discussion could take a little longer. Maybe we can do it offline in the Zulip chat, and I think there's enough space for that. I would just like to ask if there are any other questions related or unrelated.
I have a question to Barton.
Yes.
Yeah.
Hi, Barton.
Hey, Ivo.
Hi. Completely different question.
Okay.
You mentioned in your talk, very nice, by the way, about, you know, if you chose a different length, a different geodesics than that, but different L that could be implemented by a canonical transformation.
Yes.
So there comes the question: has anybody looked into this generating function of such canonical transformations, either on moduli space or in the endomorphism side of string theory? It's a question, maybe a general question, but it's just curiosity.
Well, so this is as it relates to changing vertices, is that right?
Mm-hmm.
Well, you know, I did learn something through Costello that we put in this paper, which is we did calculate finite canonical transformations in this paper. So you have a generator, a moduli space, but then you do a finite canonical transformation with it. And that analysis was a little more complicated than what I think Ashok and I did many years ago of infinitesimal canonical transformation. So maybe that would help you. It's yeah, it's section. You know, it was the issue of proving that when two vertices are proving generally that two different string vertices are a canonical transformation of each other. And this, I think we managed to do that. So I think that that's the only thing that I know. Every other analysis has been infinitesimal, but the analysis that we did together in section 2.3 of our paper is not infinitesimal, and it might give you a hint how to do it.
All right. Thank you. Thank you very much.
Are there any more questions to Barton?
This is not a question, but maybe a comment, because someone raised a question about Veneziana amplitude in Barton's setup. So yeah, I actually studied this open-closed hyperbolic vertices, and then so in the say OpenString 4-point vertex, there is one real moduli parameter, and one can take it to be the basically the length of the geodesic in the intermediate string. And yeah, and basically, yeah, there actually is a finite range one can just explicitly write down for the moduli corresponding to the region of the vertex. I was able to write down the invariant measure for the integration. So I think, yeah. So yeah, I think in principle, if one figures out the analog of Thread's work for this OpenString 4-point, then one can actually compute Veneziana amplitude.
The analog of what? Of the closed one?
So Thread wrote down these conformal maps between the usual plane with the 3-point vertex for the closed string. If one can write down analog for that thing for a 4-point OpenString vertex, then I think Veneziana amplitude is basically there. Yeah. The simplicity simply was that for the OpenString, it's just one-dimensional moduli, so it was easy enough to explicitly express the range of the moduli where it should be integrated over. So
and then you can write the formal integral for 4 OpenString tachyons, say.
Yeah. So what we need is so what we need is first, like, what is the integration measure, and then what's the range of the integration, and this specific parameter, which is the length of the intermediate strip.
Yeah.
And these two things I already put in my paper. And the other thing which is required is, of course, how to express the correlation function in the in this frame. So
did you publish this already or not yet?
Oh, no. This is actually in the old paper. So the range is specified. In the discussion section, I had one sentence about the measure.
Oh, so, I see. I missed that. Okay.
It's just a comment that maybe for Venetian amplitude, one can write it down using this hyperbolic construction. But of course, for generic like higher dimensional moduli space, I don't know what the measure should be, and then like how to express the measure with the appropriate choice of the range of the moduli space parameters. Just a small comment.
So this comment on the measure is in what part of the paper?
It's in the discussion part. It's at the very last part. So it's just a single sentence. And I mean,
but you describe the form. Do you write the measure or you don't, or you?
I wrote down the measure. So if you specify the length of the intermediate strip to be L, then the measure looks like D of cosh L divided by cosh L minus 1. But that thing I required that thing I determined by requiring that it is invariant under whether I choose the length of strip vertically versus strip horizontally. Because for the 4-point vertex, there are like open geodesics either vertically or horizontally. And we can use either of them as the measure. And I simply require that the measure to be invariant under whichever I choose.
So this is the measure for the vertex part of the moduli space. Is that right?
That is true. That is true.
For the Feynman region,
then one can go back to the cubic channel and explicitly write out the propagator with the usual Feynman rule, basically.
Okay.
And we know how this length parameterizes the moduli space and separates into vertex region versus the propagator region. So
I see.
Very
nice.
But the higher dimensional moduli case, I imagine, will be way more complicated. For example, in your case, like closed string 4-point case, it's just one more dimension, right? The twist angle. But I mean, we know the measure, which is literally the Fenchel-Nielsen coordinate, like symplectic form. But I'm not aware of how to specify the range in a simple, nice way.
I see. So you say that this measure being the Fenchel-Nielsen thing, that's what Pius and Musavian said, I think.
Oh, sorry?
The fact that the measure can be written nicely in terms of the symplectic form of Fenchel-Nielsen, it's Pius and Musavian, I think, that they did.
Right. And one thing is that is, to me, at least to me, it seems that it's specific to bordered Riemann surfaces, which is for the purely closed string case. For the open closed case, I had hard time finding some generic analog of that measure, that symplectic form, because now generically we have some both even and odd dimensional moduli space, and one wants to find out some way to write down the invariant measure in terms of some natural coordinates, which are basically the length of the strips and so on. But I had hard time finding such a measure. I couldn't find any relevant mathematical literature. And the best I could do was just writing something down for just the open string 4-point case.
Okay. Thank you, Minjay. Thank you, Barton.
Thank you.
I had the impression Yuji wanted to say something because he unmuted himself. Yuji, are you there?
Want to sleep? Maybe it's late.
Yeah, maybe.
Hi.
Oh,
Hi, Barton. Actually, I have a question. It's very, very nice lectures. And so my question was, is there any, so your previous proof of a single cover of modular space was difficult to extend it to super modular space, right? So I'm wondering if there's any hope of your discussion of the hyperbolic geometry to the super Riemann surfaces.
Right.
So that can avoid that all the issues of spurious follow of picture changing operators, right? To prove the gauge invariance of the superstring field theory. That's my question.
I don't know really. It's I really haven't tried at all to do that, but there was some discussion, I think, with Costello that you could try to do these things in group theoretical language, and I really can't tell. Costello seemed to think that there's some analog of length of geodesics coming from conjugacy classes of SL2R. So when you have a Fuchsian presentation of surfaces, that you have SL2R transformations that relate, produce the identifications, there's a whole language of length of geodesics and moduli spaces that come just from elements of those groups. And he thought the supergroup associated to Riemann surfaces, supergroup involving SL2R, could have analog formulation. So I don't know enough in order to see if anything of that was done, but I think some collaborators of him wrote a paper on that. I don't know if you're aware of that paper from Perimeter.
I see. I didn't know, but so any possibility is very important. I think so the issue of a gauge invariance of a superstring field theory is very crucial, I think. So I'm really looking forward to it. Thank you.
But there is some people that were working on that. Let me see if there's I don't know exactly, but their paper appeared a few months after our work, and I think they had some suggestions on how to extend this or apply it to superstring field theory. So I can get back to you. I can probably find those things.
If I remember correctly, that the construction of Musevian and Pius has been generalized to superstring, right? So there's a long paper by generalization to the type 2 and heterodic. So I didn't follow the paper, but I thought I had an impression that this approach can be extended to super Riemann surfaces. That's why it's,
Can I ask a related question?
Yes.
So in the bosonic string context, proving BRS gauge invariance, or let's say BRST invariance in particular, amounts to computing the commutator of the BRST charge with the various B field insertions, right, which come from the measure. Okay. Yeah. In the corresponding superstring, there are similar B string insertions, B ghost insertions, but now you also have the delta functions of the B insertions for the odd moduli, and so you have the even and the odd moduli contributions, and you have one such B insertion, B ghost insertion, or delta of B insertion for each of the even and odd moduli. So in that case, when you try to commute the BRST charge through these objects, so in the bosonic string, you find that the whole thing becomes a total derivative moduli space, and therefore the only contribution to violate gauge invariance would come from the boundary moduli space. Okay, so that's all very nice, but in the superstring, when you commute the BRST operator through all of these even and odd moduli contributions, does that also give a total derivative in supermoduli space, or is there something more subtle going on? Because there are the delta functions of the B ghost insertions that appear, which are different, which are in addition to the bosonic string. So
I think if you use the picture changing operators, then it's exactly the same. You always get total derivatives.
But if you don't use the picture changing operators and you work at the supermoduli level.
Yeah, I think even there you get total derivatives. I mean, this UG's paper and Witten's original paper, I think they basically show that you get total derivatives, if I remember correctly.
Yes, I wrote a paper with Omori, and I did a I did some discussion on this part.
Did you have to do any rigid supersymmetry shifts? Any other?
Yeah, I had a very detailed discussion about this. So please take a look at my
good.
paper.
Can you point? Yeah. Can you put the reference?
Yeah, I'll try to find my paper. So and I put my notes. Yeah.
Thank you.
I'm trying to find.
Okay, shall we finish for today?
Yeah.
So wait. I'm waiting for something to come in the chat.
Yeah, you just said it's a paper of Ohomori.
Yes, here it is. Okay, fantastic.
Yeah.
Okay, so now. Okay. Thanks, Yuji.
Yeah, I'm trying to find something for Yuji.
Yeah.
Let's see.
I think Barton is in the chat.
Yeah, I'm trying to. That's Yuji's paper, but I wanted to figure out. How do you see some people that cited our paper? Localization. I'm not sure. I don't think I can find it. These are papers by collaborators of Costello that did discuss some extension to the superstring, but I can't find it.
It's fine. It's fine if you do it later in the Zulip chat, or you can send it to us and we can do it for you.
We'll do it that way. Well, thank you very much.
Thank you, Barton.
Take care.
Thank you all, and hope to see you all again tomorrow.
Excellent.
And please come for the gather talk. Okay. Have a nice evening. Bye bye.
See you tomorrow.